Okay, guys, welcome back. Actually, hello, Amir. Welcome. It looks like only you and me today's lecture. Anyway, so quick
Hello.
announcement. We do have a class project. I already posted in the Blackboard, so we'll go over this one very quick. Give me a second. Looks like it takes time to share files here. Yeah, okay. So this is the class project that I expect from you for this year to start working. By the way, if you haven't yet decided to join group member, even if you decide to work by yourself, you have to notify me. So right now I went over the group formation form and I found out
I should be on that list.
Yeah, you're in the group too, so you're fine. Yeah. So I mean, for the rest, because I'm talking the rest of the student right now, we have group one student already told me that she's going to work alone, and we have group 2 3 members. Group 3 we have only 1 member, and group 4 we have 2 members. So the total here 3 4 5 6 7. We still have 3 students didn't decide yet. You have to decide right now. So if you want to work alone, please let me know. You have to write your name and whatever and fill in the form. It states that you would like to work alone. That's fine. You have to decide now. Don't wait. Because what the plan to do this semester or this time, so now the class project's out there. So this is the description of the class. Starting from today's lecture, we're going to see that how can we start looking at the way that how to design the database from the scratch, from the description, similar to what I give you right now. We're going to see that I give you like the timeline to require to have the 3 phases. So I expect from you, I think by this Thursday, I'm going to finish the theoretical part that's going to help you in order to start to do the phase 1. So it'll give you 1 week to finish this one. So this means next Thursday, next week, so expect from you to deliver the phase 1 with the ER model. Then, and maybe, it depends on Thursday, and maybe in the beginning of the next week lecture, Tuesday lecture, we're going to finish, I will give you the theoretical part, going to help you in order to do the phase 2. I will give you 1 week to finish this one, then after that start doing phase 3. I add more details to the phase 3. So anyway, I will add 1 folder to the Blackboard, okay? In this folder, I'm going to give you details how could you build the web application from scratch. Because in the phase 3, it required from you to do some coding. Although the coding worth around 20% for the overall score of the class project, but you need to do some coding connecting the database. I'm going to cover this one in the class, but I give you like starter hat. So I give you like in advance the way that how can we build the web application from scratch using Java. If you have an idea to do this one, this is your choice. If you decide to do desktop application, this is fine. So I give you like, this is going to be like 2 files, a set of files, zip files, and also like a tutorial 1 hour and 15 minutes. I recorded this one last semester, or last year actually. So this is going to help you to walk you through the steps that how can we create a Java application, web application using Java. So it's just for me in order to help you in order to prepare for the last phase. So remember, this weekend, I'll give you, this Thursday, we're going to finish the theoretical part to help us to build the ER model. You have 1 week to finish this one. Tuesday, we're going to finish the requirement for the phase 2. That means we have 1 week to finish this one. Then after that, the rest of the semester, you have up to the end of the semester to finish the phase 3. There's some parts you're going to see, as you note here, some of them are going to be like extra credits. Okay, so pounds. If you do this one, you see that, let me show you here, that, for example, there's some pounds here. If you do that, they'll give you extra credit in the top of 100. Okay, so you have a chance to get into some pounds here if you want. Okay, that's all about the class project. So let me go back here to the slides, and I want to go over what we did last lecture. Okay, give me a second. I want to go to the right slides here first. Then after that, yeah. So what we learned so far last time. So at the last week, I first introduced you to the principle of the database system in general. We define a database as what? as a collection of data that's related together in some way that's trying to model some aspect of the real world. So related data is going to relate to each other. So for example, university, you're going to find that information related to the university. Okay, you can have information about the student, information about the instructors, about the classes, courses, and etc. Of course, you're not going to find information about, to say, your social, work information, etc. for the student, or your personal information, etc. I mean, the relation that doesn't relate to you. Or maybe, let's say, maybe it's not a good example, but let's say, information about your criminal record information, etc. So it's not related to this kind of information. Okay, we define a database management system, which the system you're gonna do what? It's gonna have what? Collection of store the collection of or store the information of the database itself, plus provide us with the set of software or tools which allow us in order to modify, and say handle the data stored in the database management system in a more efficient and convenient way. That's what we did here. Okay. Then after that, we start looking at the fundamentals of the relational model. Okay, that's what I'm going to try to summarize what we did last time. Okay, so we said the data model is defined as what? As a collection of concepts for describing the data in the database. Because I want to find a way in order to describe the database in general. The same thing, now we have a class project description. You need to figure out the way, how could you describe the data that we have? How could you represent the data somehow in the way that everyone can understand what's going on? Okay, so in this case, we're going to describe how the data is structured, organized, how the data, the relationship among this data. We're going to more details today. They're going to be much clearer when you cover the ER model, the way how to start to design the database. Then after that, we need to define the data constraints, which we can simply define them as a set of rules that you wanted to enforce in our data. For example, you can say the GPA must between 0.00 and 4.00. The student, for example, or the student ID or student department must be a list of these following departments. Or the semester must be fall, spring, and summer. This is the only semester. There's only value available or allowed in order to have this, say, fall, or let's say, semester. It looks like I lost the connection. Hopefully not. Anyway, I'm recording the class in case we lost the connection. So we define a data model, which, I mean, this is, when you define, you have trouble sharing your audio. Did you hear me, guys? Can you hear me? Can you hear me, guys? It looks like I lost the connection somehow. I don't know. Okay, great.
It works for me.
So great. Okay, so we define a data model. Then we have one example of the data model is called the relational data model, which is the one that we're going to use here. Okay, so this data model is going to have what? Which define 3 concepts in general. That's what we did last lecture. Okay, so it's going to define 3 concepts. The first one is going to define, for example, the structure. In other words, what do we mean by the structure here? This means the definition of each relations that we have and its content. You're going to say, for example, okay, it looks like we have 3 tables. The first table is about the student. It's going to contain the following information: student ID, name, and GPA, department, something like this. And also, what's the data type of each attribute. Then after that, we're going to say we have instructor, and this is the information about this instructor, or the types of information. This is the structure of the data. Then, it's going to define this relational model in general. Okay, the second concept that be defined by the relational data model is the integrity. What do you mean the integrity? Which is a set of rules that ensures that the database contents, when you say inside the database, satisfy the constraint. And how can we get this set of constraint or set of rules? It depends on the domain that you try to build. For example, I can specify some set of rules based on the university, okay? So, database. So assume that the GPA, in our case, must be greater than 0.00 and less than 4.00, right? And the grades of the class is going to be A, B, C, D, for example. We have a specific letter that's going to be only allowed a set of grades. So we don't have A plus, for example, or B plus in our university system, right? So in this case, you can specify what's the set of rules that must be satisfied in your data. That's what the meaning. So that's if you're wondering from where we can get this set of rules. And the third one, or the third concept, is going to define what? The manipulation, which is the way that how can we access the data, how can we manipulate the data. We start looking all these stuff last time one at a time. So we show you that we're going to use the relational model with the way how in order to, let's say, define the structure of the data, okay? So how can you define the structure of the data? We said the data is going to be three things, yeah? It's going to be construct as what? As a table. So if we have a relations, or they say whatever an entity, for example, student, instructor, etc., we can store this one as a table here. Okay? So relational databases store data in the form of the relational tables. We do have, like when you say the table database looks like we have a tuples and we have a columns. A column is going to be specify an attribute or set of attributes uniquely identify this tuple. For every single tuple, we need to have a set of attributes going to unique has specific value for each tuple. Then after that, we can specify a set of attributes which are going to be uniquely identify this tuple. For example, for what kind of attributes, maybe you have a question, how could you get these attributes? This is going to depend on the design of the database. We're going to learn how to collect this information. If you take a look to the class project description, you can figure out what kind of attribute the one of the user, of the applications, or the domain expert that looking for. We wanted to have this set of attributes that can be stored in the database. So in this case, for the student, we know the student ID, name, and GPA, and the department. Those are the information that we're looking for. We talk about two different terminology. The first one, we call this one the cardinality, which is going to tell me how many numbers of tuples in this relation. And the archery, or to say the degree, with the relation, which is going to tell me how many or number of attributes of this relation. We're going to use this one a lot. Clear? Then after that, we said that attributes might be unique in general case, or atomic action. What do you mean that? By the way, the name of attributes must be unique within this relation. So we don't have these two columns going to have the same name. So in this relation, you are not going to find ID, then ID. No, it's not allowed in the relation. We have two columns in the name of a column or attributes. It's not unique. Must be unique within this relation. Okay? Then after that, we talk about the domain, with all the possible value or allowed value for specific attributes. Yeah, of attributes. For example, if you assume that of course, we need to define an attribute, we're going to specify what data type. It's similar to the programming language. When you declare any variable, okay, you can specify, you say the variable integer. So what's the domain? What's all the possible value for the integer? It depends. For example, assume that it's going to be 2 bytes. So we have two, I think, or 1 byte. Assume that it's going to be to the power minus 127 up to the power 127, something like this, yeah? So you know that what the possible value of the allowed or legit value that in this domain. For example, assume that the semester in our case must contain only 3 values. Summer, fall, and say spring, yeah? So in this case, what the allowed value is going to be summer, fall, or spring. That's the possible value. And etc. So we said that attributes must be atomic. What does that mean here? This means we cannot break it down. So in this case, we don't have this kind of attribute can be part of the relation in the relational model. So for example, you cannot say name, and name is going to be first name, middle name, and last name. We call this one a composite. We don't have this relation. No, it's not allowed with the relational algebra. So in the relational data model, we are going to go over this one more details, but right now it's just what I want from you to understand what's going on. When I say this atomic, it's not composite. It's not something like this. It is not multi-valued. So in this case, we don't have, for example, the phone ID, which one attribute in this relation. And the phone ID is going to be, say, phone number, 1 phone number, 2 phone number, 3 phone numbers. It's going to be 3 different values. Multi-value is going to be stored in the same attribute in the same tuple. It's not allowed in the relational data model. We do have a specific value. We call this one null. It's going to be in everywhere in any domain with the null value. It's going to cause us some troubles, but we're going to see how can we handle that later. Okay? That's the main thing actually talk about last time. Then we have a schema and we have like instance. We covered this one before. Then let me see what we need to, I need to talk about the integrity constraint a little bit because I wanted to make sure that we understand what do you mean the super key, primary key, and the candidate key. Okay? This is the way, just mathematical notation, how can we represent a relational schema. So, generally speaking, we have a relation R, this is the schema, and here you just specify the list of attributes of this relation, of this schema. Okay? The keys. We talk about the keys, right? What do you mean by the keys here? The keys is the way that in order to help us in order to identify any tuple within this relation. An instance. You give you an instance. What's the current value? This relation. So set of relations. Then you need to figure out a way how can you uniquely identify a tuple or student. So it looks like we have maybe one or more attributes. It depends on the relation that we have. Sometimes you maybe require only one attribute, maybe you require two or more attributes. Sometimes maybe you require all the attributes of this relation in order to uniquely identify any tuples here. Why you need to perform this one is going to help us in order to perform what is called the integrity constraint. I'm going to go over this one more details with the time, okay? Right now, what I want from you to understand when you talk about the integrity constraints, this means this is a way in order mechanism guard against accidental, say, damage to the database. How can you do this one? By ensuring that authorized change only that has been made to the database. And it's not going to result to say to the loss of data consistency. So it looks like a set of rules you need to enforce in the whole relation or the instance of the database. One way or one kind of integrity constraint you need to enforce, one of them is called the domain constraint. What does that mean in this case? So you can check, make sure that it looks like you can check your if statement. If anyone tried to modify, let's say the GPA must be between, I need to check the value of the GPA, make sure that is within the domain. It's within the value between 0.00 and 4.00. If someone tried to insert the data above this value or below this value, so I'm going to reject the entry of the X. I'm going to talk about this one later, but just right now, think about this set of rules to enforce to make sure that data will be in consistent state. And I'm not going to damage the database itself. Okay? So here, I need just to talk about the super key. What do you mean the super key? With the set, when I say set, combination, one, more, two, whatever number of keys or set of attributes that specify that can uniquely identify any tuple of this relation. What does that mean here? There is no two tuples in this instance of this relation can agree on the value of the set of attributes that are specified. So I call this one a super key. We give you many examples, I believe, in the last lecture, but again, I'm going to emphasize, I'll repeat this one because I need to make sure you understand that. So assume your relation R, it maybe has ID, name, and GPA. And let's say student action. I'm going to say here the ID and name and GPA are super key. Are you agree with me or not? The ID, name, and the GPA, all of them together is going to form super key. Do you agree with me or not? What do you think? It's super key. Why? Remember the definition here. There is no tuples. It's going to agree in the same value of the ID, name, and GPA. Since I do have ID, name, and GPA, this is the only three attributes. So in this case, exactly, there's unique. There's no two tuples going to have the same value for the set of attributes. This is super key. So how about in this relation, let's say ID and name? Is ID and name super key or not? Yes. Because remember, we assume that there is no tuple going to have the same student ID. Do you think that we do have two students that are going to have the same A number? No way. In the same university. So this one too. As you said, you want. Yeah, it's unique. Or there's no two tuples going to agree in the same value based on this set of attributes. So check any tuples here. Check whether the value of ID name or value of ID name is going to be never going to be have the same value. Then after that, do you think this one is a candidate key or not? A candidate key have a special definition. We said the candidate key is going to be super key but it's minimal. What does that mean? It's a super key, but cannot be break down to the another subset of attributes, which is going to be any of them is going to form a super key. Let me talk about this one here. So check this one. We said this one, the ID and name and GPA are super key. We agree. Do you think they are candidate key? No. Why? Because I can break it down. It's not minimal. It's not the smallest subset that uniquely identifies the tuple in this relation. That's the meaning. It's not the smallest subset. It's a subset of that. So in this case, you can say break it down. You can come up with ID and name. And ID and name are super key, as we said here. Right? It can be break it down to the ID and GPA. And the ID and GPA is super key because there is no two tuples is going to agree in the value of ID and GPA. Remember that, but here the ID is unique. Then actually, this ID here. So here, I break it down to at least, 3 different. I can't do this one more. But in this case, yeah, 3 subset of 3 different keys. Each of them can represent or can form a super key. So this one is the super key, but it's not candidate key. Okay? Clear? So how about the ID? Is the ID candidate key? Yes. Can you break it down? No. It's the minimum small subset that I can come up with. Okay? Sometimes it depends on the relation. You need to have two or more attributes in there specified. But I wanted from you to know super key. Okay, I know this one. Candidate key is the super key at the same time is minimum. Cannot you break it down to the subset of attributes? At least one of them is gonna form a super key. Okay. So what about the primary key? Sometimes you end up we have multiple candidate key. Now, when you have a multiple candidate key, for example, let's say, the nice example here, the student ID and the social security number. So the ID by itself is candidate key, right? A social security number is candidate key. If we assume that every single student must have social security number. This is the assumptions. Or actually, I can add another extra, say, requirement definition of the candidate key. The candidate key can have a null value. So in this case, even if we don't have a social security number for every single student, I can have a null value. So it looks like we have 2 different candidate keys. Sometimes you're gonna end up, we have multiple candidate keys, and in order, it depends on the domain requirement, or it depends on your definition, or it depends on you, you have a freedom to choose which one will be the primary key. So the primary key is the key that you use in order to uniquely identify any tuple of this relation, which must be candidate key. Of course, it must be candidate key. That means it must be minimum. Okay. So again, sometimes you're going to end up, we have multiple candidate key. You choose one of them as the primary key. Okay. We talk about the foreign key constraint, which is another way in order to let's say, one part of the integrity constraint. Actually, in the formal definition, we do have a referential integrity, which ensures that a value that appears in one relation for a given set of attributes also appear for the certain set of attributes in another relation. Here it might be any attribute, but most database management systems don't implement this one. They're going to implement the foreign key constraint. What does that mean? The foreign key constraint is the subset, or say a special case of referential integrity. The foreign key constraint, sometimes you need to figure out a way that you have one attribute might be 1 or 2 attributes in relation R, for example, must be a key or mapping to another relation, in another relation. So for example, assume that attribute X and R, it's going to be a foreign key constraint. That means, or let's say department name, and here let's say user student. Okay? Information department. The department is a foreign key here in this relation student. Why? Because this is going to be referred or mapping to what? To a primary key. That's the meaning of the foreign key constraint. It must be a primary key or unique key for the reference and relation. In this case, it may be the department. So what does it mean here? When you have this kind of constraint, I can guarantee the following. Here, I will never have a student that belongs to a specific department where this department was not listed as a department or the set of departments that in this university. Makes sense a little bit? Because I need to figure out, because right now when someone tries to perform insertion and deletion, I need to make sure that when someone inserts a new student, and this student is going to say department XYZ, when you try to insert this one, I need to make sure that there exists department called XYZ in the university database. In this case, this information can be held in the department relations. If there is no exist, so the system is going to be rejected. The insertion going to be, it's not allowed. Remember, we have a set of rules. Try to make sure our data is going to be like what? It be consistent. I'm not going to lose information. I'm not going to lose the consistency of the data. Make sense to you guys? That's what we said last time about the Key Constraint. Let me go over this one again, this example. So that's a nice example. Assume that's a student relation. How many super key do we have? Many. One super key, all the relation attributes. That's one thing. The other one is going to be ID name, or ID address, or ID phone, or ID GBA, or a social security number name. I mean, any combinations. All of them is going to be the super key. How many candidate key do we have? It's going to be only the ID and the social security number. So you have two candidate key. Which one you're going to use? I'm going to use the ID because I'm sure 100% every single student is going to have a unique ID in the university. We cannot guarantee every single student have a social security number. That's why we, eliminate this choice. And also for the security reason too, because I don't want to use the social security number as the key in order to access the data, etc. Okay, so it does make sense if you try to log into the system and going to say, okay, provide me with your social security number and the password. Can I give you my username and password? No, username is your social security number. So even for the security reason, it's not a good choice. Okay, take a look at the course here. We're going to contain all the information about the courses here. We have a course ID. We're going to have the course number. So we have a unique name for the course ID. We do have a course number. And this is the name, the title, the credit hours, and etc. for this one. Okay? So the super key might be all the attributes. The candidate key might be, let's see, the course ID or the course number. Okay? Either is fine. I'm going to use the course ID unique identifying attribute. Either is fine. Okay? Usually in our university database, we're going to use the course number here. But in this database or this example, they have a course ID. This have a course ID is unique identifying any tuple in this relation. Good. Now assume they have a grade report. What do you mean the grade report? I need to list, okay, and this information, this table, I'm going to keep tracking for all the courses taken by every single student in which semester, and also with the, I need to register or add to say the grades the student takes or got for every single course. Then after that, when you print out the information, you can get access to the table, get information about the user, and get, maybe print out the transcript of the student or this user. So what did you notice here? We do have ID, course ID, semester, and grade. Why I need to, first of all, why I need to choose all of them and gonna be a key of this relation? Can I say the ID and the course ID, they are the only option, they're the only values that we can use or attributes use as a candidate key here, or the primary key of this relation? Why you need to add a semester here? Because, in other words, can I say the primary key is the ID and the course ID? Or the key of this relation only the ID or the course ID without the semester? Think about this one. If you use ID and the course ID, can you uniquely identify any tuple in this relation? No. Is there, because why? Because you take a look at this one, definitely we have a student, specific student, maybe this student take this course multiple semesters. He failed this course last semester, then it's going to take this course another semester, etc. So I need to register the course ID and the ID of the student, and I need to register also the semester when this student take this course. So in this case, I need to have the three attributes to be the primary key of this relation. Make sense to you guys? I believe so. That is from my point of view. don't hesitate. You can say, no, you're wrong, I didn't get it, and what the hell are you talking about? Feel free to say anything. So it's clear with you, to you guys? Great. Just I need to make sure that you follow me. So that's what we did about this one. So now we need to perform this one. So that's the most important thing that we covered that part. So this is the schema diagram of the database. Just explain what's going on. We tried to build something similar, use the ER diagram. We're going to talk about this one later. Then after that, we take a look at data manipulations. I'm not going to go over this one more details. The only thing I need to talk about here, we talk about the way that how can we access the data. So we know three things. Remember three concepts? The structure, define the first one, define the structure. The second one, define the integrity. The third one, define the way how can we access the data. We'll give you example using relational algebra. Okay? What's the relational algebra? The relational algebra is defined as what? Is the fundamental operations in order to allow me to retrieve and manipulate tuples in the relations. So it's based on the set algebra. Okay? So it looks like in this case, each operator is going to take one or more relations. So you're going to see it depends what kind of operation. Some operators are going to allow me to access the data from one relation. So required to have only one input. Some of them try to perform union, cross product, and join, etc. That means to access two or more relations. So it's going to be one or two, okay? So it depends. For example, select whatever from the relation R, there's 1x, okay? Or, by the way, I'm going to use sometimes tree expression in order to make sure that, we're on the same page with the different ways. How can we express, how can we represent the relational algebra? If you understand the relational algebra, you don't have any problem to understand the sequel. By the way, the plan to post the first homework right after today's class. The first homework, I'm going to try to test you, try to give you a chance to practice the relational algebra. Okay? So, again, each operator take one or more relations as input and output, and new relations. When you perform this one, you're going to have a new relation here. This new relations, I don't know about the name. I'm going to show you the way that how can we rename this one using different names. I can use this one as an input to another relation. So you can perform, for example, selection. Then after that, you can perform projection or whatever. Or maybe you can perform join with another relations, etc. You can continue doing this one. We start looking at this 6 basic operators: selection, projection, union. I guess we finished union last time. So selection, just to remind you, is like what? Filter out the tuples from the relations. Just take a look at the relation and say, okay, do we need all of them or not? No, I don't need all of them. So it looks like we have if state access this relation. Let's say selection. We have a predicate over the relation R, or if you prefer, write this one as an expression like this, relation R. Yeah? I know what about the predicate. That's means a condition. So it looks like in this case, you're going to access the relation R tuple by tuple. For each tuple, you need to check whether this tuple is going to satisfy this condition that you specify in the predicate or not. If yes, this tuple is going to be part of the result. If not, ignore this tuple. In both cases, jump or try to perform the same operation for every single tuple of this relation. Great? That's what we did in the select. Select is going to define what? It's going to change the number of the cardinality of the relation. That means the number of tuples, somehow it's going to be less than the number of tuples of the relation R. Because here I'm going to filter out the tuple that doesn't satisfy the condition here. Right? Maybe there's some cases that maybe you're not going to filter out any tuple. You're going to produce the same relation. So it depends on the predicate that you have. But in most cases, I'll get this one, reduce the number of tuples. How about the degree of R? Are you going to change the degree of the relation or not after you perform the selection? What do you think? Are you going to change the degree of R after we perform the selection or not? Yeah, by the way, don't expect for me to ask you questions. Definitely I'm going to ask you. This kind of give me a chance to catch my breath. Take a rest for a few seconds. So what's the degree of the relation R? The artery of the relation R. Number of columns in the relation. Do you are going to change them? No, it's going to be the same. So I'm not going to change this one. It's going to be the same. So the number of columns is going to be the same. The number of tuples with the cardinality, yes, it's going to be less. We cannot guarantee it's going to be the same. Projection. What do you mean the projection here in this case? Projection just means in this case, we're going to ask the relation. I'm not going to filter out based on the tuple. I'm going to reduce the size of the relation. Instead, produce or you say display all the tuples or all the columns of this relation. I need to specify a specific column. I need, for example, I want only the ID and the name from the relation R. Yeah, so I can say project the ID and the name from the relation R. That's my condition. So in this case, the cardinality is going to be the same, but the degree of the arch of relation R is going to be different because the degree is not going to have 2. Because why? We have only 2 columns. Then after that, we take a look how can you perform the union. Of course, we can join them. You can perform selection with the projection. You can put all of them together. You can specify. You can come up with what's called, say, different comparison, and the predicate might be greater than, less than, not equal, etc. We have different ways to perform this operation. You can have like combine several predicates into large predicate by using the connectives. For example, you can say condition 1, predicate 1, and predicate 2, or predicate 3, or whatever. You can do this one together. Okay? Union. We said the union. I guess the one that is stopped here is slide 36, I guess. In order to perform a union, go over this one again because it has very important, condition here, or the property. In order to perform union, that means you combine 2 relations together. So assume this relation R is going to have A, B, and the relation S, A, B. For example, 1, 1, 1, 2, let's say 2, 1, 2, 2, something like this. In order to perform R union S, there is a condition. Okay, what's the first condition? The number of the degree or the arch of the relation must be the same. So this means I have 2 columns here and they have 2 columns here. I don't care about the names. But right now, the most important thing, the columns must have the same number. And the second one here, we do have the data of the column, the corresponding column must have the same domain or the same type. In order to join them, in order to have a meaningful result. We call this one the union compatibility, or must be compatible, or the union compatibility. If you have the relation doesn't have the same, not equal the same name, then in this case I'm going to use the name, which we're going to go over this one later. Okay, so let's have this example. Union are this one. So you take this relation. Well, by the way, when you say union, that means you try to perform what? You try to generate a relation that contains what? All tuples that appear in either only one of or both of the input relations. So either it's going to be only in one or in both of the input relations. When we say input relation, I'm going to talk about the R and S in my examples here. Okay? So I have here and you have here. We don't have a duplicate. Why? Because we're talking about a set algebra. Sets, that means we don't have a duplicate of the data. If we have a duplicate, we have to eliminate it. Okay, let me give you an example why we need to have a union compatibility. Assume that we have the R is going to contain this information here, and you say, oh yeah, the nice thing is say R is going to have, let's say, ID and the name, a student ID, student name, for example, and S maybe it's going to have like student ID, student name, and let's say GPA. Can you combine them together? Can you perform union? No. Why? Because the cardinality is not, because the degree of the arch is not the same. Here we have 2 and here we have 3. What does that mean? When you try to combine them here, somehow you end up we have something like this. Your R union S. This is the information from the relation R. For example, this is the tuple ID and the name. Then I'm going to use a different color. Now I need to join combine the information from the relation S. So it looks like we have the GPA. Does that make any sense? No. We cannot perform this operation. That's why this is the condition that we have. We have the same number of attributes of both relation, or they have a meaningful result. That's the one thing. So how about the other condition? That when we said that we must have the database, the 2 relational schema must be compatible. That means A must, for example, A, and A must have the same data type, and B must have the same data type. So I will give you that one example here. Assume that we have the relation R is going to be, try to come up with, the ID and the name. And the relation S is going to be the ID, let's say, the department name. Can you join them? Can you perform union here? Someone is going to say, okay, we have two columns, it's fine. But this data doesn't make sense. You can combine them, but the system is going to have a confused. Assume, especially if you define the department name and the name is going to have the same data type. For example, assume that it's going to be string, okay? Right now. Although we're going to use a varchar, etc., but we said the string. Both of them is going to be string, and assume that we have 20 bytes each. Can I join them? No. Why? Actually, you can, but you're not gonna get meaningful result. Or result makes sense because you're gonna have, for example, ID 1 and name Alice, and ID 2 is gonna be Pop, and maybe you have 1, let's say, or say it's gonna be computer science, 2 is gonna be math. When you join them, it will be both this one here, both of them in there. So 1, 2. The other one is gonna be computer science, and it's gonna be math. Do you end up with have meaningful results? Interesting. Take a look at the name. What do you mean? The name of Alice, Bob, or computer science and math? So see that? That's why the must have the same data type and the same domain. Yeah? Different names, it's okay. We can handle this one, but must have something have the data types. Clear? Okay. Let's take a look. How can you perform, let's say, the second one is one. It can be project. We did this. Give me a second here. Just I want to make sure that's in the right place. Projection, we did this one. Yeah, I need to go union. Just I want to make sure that we're not loss. Okay, union. Okay, give you an example. This is another example, and this is another example. Yeah, I like this one. So sometimes because you find all the courses taught in the fall 2009 semester, or in the spring 2010, or in both. Remember, we said a union means that it can be generated relations that contains all tuples that appears in either only one or both of the input relation. The one or in both of the input relations. So it looks like I'm going to perform union. So the simple one, give the query, give you the all course taught in the fall 2009 semester, union with the course in the 2010 semester. Then you are fine in this case. And that's what we did here. Okay? You can do this one, by the way, here. You can say select semester. I'm going to use shortcut of the fall. And it says semester or year equal 2009. Then you can say, or it's going to be semester, spring, and year equal 2010. So in this case, what we did, take this one, this part, and said, or this part. Yes, you can perform this operation, but make sure that you have a parenthesis, something, or something else. Can I do this one? Yes, because either it's going to be here, or either it's going to be here. Either of them is going to be satisfied the condition, that's fine. The reason why we can do this one or this one, sometimes you might have an index. Maybe you have index only based on one attribute of this value. So we have two different index. We can use them in order to speed up the data. Okay. Now take a look at the set differences here. What does it mean here? I'm trying to generate relations that contains only tuples that appears in the first and not in the second input relations. So in this case, it looks like we have R, or let's say R minus S. Okay? That's why I said in the first relation, but not in the second relation. It's written as R minus S, something like this. So it's going to be tuple that belongs to relation R, but not belongs or doesn't belong to relation S. I mean, let's say, set operation, which is going to be covered here, which is going to be union, difference, and later intersection. Three of them, all of them must be satisfied the condition that have union compatible, or the compatibility. That means they must have the same artery between two relations, and also attribute domain of both for the corresponding attributes must be compatible. Otherwise, we cannot do it. So here in R but not in S, so it looks like we have alpha 1 is in R but not in S. That one, alpha 2 no, because it exists here. Beta 1 in R but not in S. So this is the result that you end up with. Remember, if you have a duplicate value, you need just to eliminate them. Okay? So, just to have this example, find all the courses taught in the fall 2009 semester, but not in the spring. So, it's going to be here, if the course is going to be taught in the fall 2009 fall semester, it's not going to be in the spring 2010. So, the simple thing we can perform here, we can use, set difference. By the way, there's many ways. This is a simple way in order to perform that. So in this case, in order to do this goal, get one query, all the that satisfy this condition, list of the costs in the fall and year 2009. I need just the cost ID in order to reduce the sample of the data that you work with, okay? Minus the lesser of the cost that's going to be offered in the 2010, spring of 2010, which give me the condition. Okay. Cartesian product. Sometimes, right now we have one relation combined with another relation, etc. But sometimes you need to retrieve the information that are required from you in order to access more than one relation. So it looks like I need to concatenate this relation, one big relation. Then after that, you starting extract the information that I'm looking for. Okay. So in this case, I'm gonna give you like a simple way how to do that using Cartesian product. Okay. The Cartesian product is, or they say a product in general, is generator relations, or one relation, that contains all the possible combinations of the tuples from the input relation. Let me give you the simple example. If you have a relation R, Cartesian product with S, I'm using the X product in order to notate, or to represent this kind of operation. Okay, so what does that mean here? That means in order to perform this one will produce a big relation. So in this case, you take every single tuple belonging to the relation R, and you need to concatenate this one with every single tuple S belongs to the relation S. So in this case, you end up, we have relation R and a tuple from the relation R and tuple from the relation S concatenated together on one relation. You need to perform this one for every single tuple for relation S. Then after that, you have to repeat this operation for every single tuple from the relation R, and this operation is going to be concatenated with every single tuple of relation S. So in this case, if you have one, I would say n tuple of the relation R and m tuple of the relation S, you end up we have n multiply m tuples of the when you perform R Cartesian product with S. The artery, or the degree of each tuple is going to have what? The schema of the relation R plus the schema of the relation S. So concatenating, not combining, but it in one big, larger tuple. Okay? So assume that if the attributes of the relation R and S are disjoint, we don't have attribute has the same name. So in this case, it's fine. But if you have an attribute have the same name, that means we need to find a way in order to distinguish between them. Okay? I need to use renaming. Or sometimes, this will give you an example here. Assume relation R has, AB, and the relation S is going to be AC. When you perform R Cartesian product S, this is the schema. It's going to be A, B, AC. But the problem now we have A and A. So in this case, either I'm going to use renaming, or I'm going to use the relation name as what? As a prefix. I'm going to use R.A here and S.A here in order to distinguish that between the value of attribute A here with this A. This belongs to the relation R, and this attribute belongs to the relation S. So that's what we said in the R is going to be relation R and plus the number of columns of the relation S. Clear? Good. So let's have an example here. Just a quick example to see how it works. So R and S, okay. Do you think you have the union compatibility? No, we don't have a problem. the thing you're going to perform what? Now, for every single tuple here, you're going to be concatenate with every single tuple for the relation S. That's what we did here. This is the result of this operation. So alpha 1, alpha 10 plus, alpha 1, alpha 10 plus, alpha 1, beta 10 plus, alpha 1, beta 10 plus, and etc. Then after that, for the second tuple, for every second tuple relation, I'm going to perform this way with every single tuple of the relation S, which is going to produce the second part here. Just to give you an example, beta 2 is going to be beta 2 alpha 10 plus, beta 2 alpha 10 plus, and etc. So assume that we have 2 tuples here, and we have 4, then we end up, we have 8. Yeah, 2 multiply 4. So we have 4 plus 4, so we end up with having. This is the Cartesian product. We don't like this one, by the way. So the Cartesian product by itself or alone is not a good idea, because we need to add something else. In order to clarify this one, let's have the next example here. Actually, the actual example we talk about the instructor and the teacher together. You can perform a selection or whatever, any kind of operation after you perform, let's say, product. Yes, you can do selection, you can do projection, whatever you want. It depends what you're planning to do. But as you mentioned, just speaking, most of the case, Cartesian product must be followed by selection in order to get a meaningful result. So if you said Cartesian product S, and so after that perform a selection. The nice thing, in order to perform this one, the system is going to say, okay, I'm going to take the relation R, okay, and S, this and R, but perform Cartesian product. Then after that, the result, I'm going to perform the selection, A equals C, and this is the result going to be produced, something like this. We're using tree structure going to help us in order to understand how the order of the execution. And remember, we talk about the relational algebra as a procedural language. What does that mean? I'm going to give you the exact steps, what you're planning to do. How can we, this is the result I'm looking for, then I'm going to show you exactly how could you get there. They said, go to the relation R, perform Cartesian product, then after that perform selection, then this is the result going to be produced here. Okay? So here they perform the Cartesian product, this is the step here. Then after that, I'm going to perform a filter out the tuple. I mean, make sure the A is equal C. So the column A must equal the column C. In this case, this one. And you have starting filter out the data and reduce the number of tuples going to be part of the result. So 1, 2, 3, which those tuples going to be part of the result only. Okay? Hopefully so far so good to you guys. Let's think about the Cartesian product that we have instructor with the teach. Instructor with information in the table that contains all the information about the instructor of the database, the university database. Teach and they'll have all information about or keep tracking all the courses taught by every single instructor in the university. When we perform Cartesian product with instructor the teach, we're gonna have a common attribute between them, right? We have instructor ID here, and the teacher is gonna keep information about the instructor. We're gonna see that the teacher is gonna contains the ID of the instructor. We perform Cartesian product, so in this case, the ID of the instructor, ID of the teacher is going to be part of the result. So what we need to do here, since both we have more, let's say, 2 more attributes, or 1 attribute at least, have the same name, or have a common name, or repeat it twice, we need to add, the relation name as a prefix in order to distinguish between them. Because if we say this ID and this ID, okay, in the relation, so this value is what ID, and this one belongs to what ID. ID is what? I cannot tell which ID belongs to what relation. This is the ID that belongs to relation R, or the ID belongs to relation S. Especially if the attributes have, 2 or more relations are going to have the same set of attributes. Okay? So this is a relation structure. This is a teach. When you perform this Cartesian product, I want from you to see something. Of course, you're going to say, oh, there's a mistake, a huge problem. So I'm going to join this one with this, with this. With this, and this we have a different color here. You see what's happening here? Because I'm going to take for the first tuple, just take a look first tuple. That's what I'm going to join this with every single possible combination here. Okay? Here, since we have ID here and the ID here, I'm going to use something somehow to say add the relation name as, let's say, prefix to not distinguish between them. So far, so when you perform the Cartesian product, of course, the black arrow identifies that there is a problem. Why? Because what I'm doing here, when you combine these information, one relation, big relation, now I connect this ID with this guy with the course that this guy never teach, because in this case 10101 this professor teach only those 3 courses. When you do the Cartesian product, now I join this instructor with the course that never teach or never taught, right? Because this is the Cartesian product. For every single tuple relation, the first relation can be joined or concatenating action with every single tuple of the other relation or the other part. So that we end up, we have something, huge tables here. So you see, this is the problem here. And also, this is the problem for the other one. And those are the problems, actually the whole thing for this guy. And those are set of tuples. When I say set of tuples, that means the whole thing, okay? With this guy. So what happened here? Most of the resulting that we have, or tuple that we have information about the instructor here who did not teach a particular course. Does that make any sense? No. That's why I'm keeping saying, when you say Cartesian product by itself, it's not enough. You have to do somehow selection. Because if you do Cartesian product, you're going to end up, we have too much information, join things or concatenate things that's supposed not to concatenate to others. Okay? So in this case, in order to get only the tuples that instructor will teach that pertain to a specific instructor, in other words, and it only keep tracking the list of the courses that teach by every single instructor, no one else. I mean, it does mean associate the list of all each instructor with the courses that already teach by this or taught by this instructor, nothing else. So what I'm gonna do is, what if after perform this one, if I say select, let's say the ID is equal to ID. When I say the ID, I'm going to say the instructor ID with the teach ID. I use I and T just for simplicity. If I did this one, that means in this case, I'm going to make sure that after before Cartesian product, in order this one is going to be part of the result, the instructor ID must equal teach ID. So in this case, I can only combine or have information about the instructor who did teach a particular course. So keeping in your mind, Cartesian product, you have to perform selection in order to avoid this kind of problem. What I've said is specified here, so that what we did here, when you perform this operation, I've said selection, instructor ID equal teach ID, after perform the Cartesian product or product, now we end up, you see that, all these guys here, okay, we only have information about the courses or about instructor who did teach a particular course. Clear? You are quiet. That's the problem, because they give you holiday yesterday, off day. So everyone think about Saturday, Sunday, Monday. Maybe this guy is not gonna be appear today, so we're gonna maybe Tuesday, Wednesday. Yes, we're gonna have a class Thursday. No, I'm here. So anyway, I assume that you follow me, okay? If you have any question, please feel free to interrupt me. We do have another relation called rename. What does that mean, rename here? Rename is going to help you in order to do the following task. When you do the relational algebra expression, when you say, for example, R Cartesian product with S selection, whatever, the result of the expression is going to be of the result of relational algebra. It's going to be a relation, okay? But this relation doesn't have a name. I don't know what's the name of this relation. Because you take R Cartesian product with S, then after that do whatever operation, even if we don't have an operation. Or if you said selection of the particle of the relation R. What's the result? I don't know. What's the name of the result is relation? It's not relation R. It's something else. So sometimes you need to give the result of the relational algebra expression that we have a name. In this case, we're going to use rename. It's going to help us. Okay? So allow us to know the name. And therefore, once you name this one, we can use this one in order for further computations. So here in this case, I can say, okay, I do have expression, for example, selection B of the relation R, Okay, then let's use a different color. I'm going to use the rename. I'm going to call this one as X. So what does that mean here? You take the relation R, perform a selection, and the result going to be stored in another relation called X. I'm going to use row. Okay, that's the way how can you perform. So now we have another relation S, X, where it contains the result after you perform selection or whatever the result that you're going to perform. Clear? It's also sometimes allow you. Sometimes you're going to refer to the relation by more than one name. For example, I'm going to give you an example that requires from us in order to access the data from the same relation twice. So I need to concatenate the relation and the data from this relation or relation with itself. Then after that, I need to perform another computation. That's going to happen many times. So in this case, when you perform two Cartesian product, the best thing you're going to perform here, take a copy of this relation, assign to another name, then now it looks like I'm using two different relations. They have two different names, actually. Okay? So either going to be refer to the result of relational algebra or maybe rename a name of the relation. Okay? Which have a copy of the relation that can be renamed to another name. Okay? So we have different ways in order to perform that. Generally speaking, this is the general form, row X of the relation E. So that means, expression. Whatever expression you have, selection, projection, whatever kind of operation, the result can be stored in what? In the relation X. How about the attributes? The attributes is going to be the same. I don't know what the expression is going to produce. What kind of attributes? It's going to have the same name. The only thing we can produce or create this one or put this one under the name, new relation called whatever, X, Y, Z, whatever the name that we're going to specify here. Clear? The other thing here, what if you want to modify the attributes too in this relation? Either you're going to modify the name or the attributes. So assume that relation expression here produce, for example, attribute B1, B2, B3. I don't like B1, B2, B3. I need to use A1, A2, A3, different names. So in this case, I'm going to rename, for example, whatever here, assume the expression here, and I'm going to specify, do you want to, on the rename, you have to give the relation name. I'm going to use C. I like C, relation C. Then attribute the first, since we have three attributes, the first one is going to call A1. The second one, do you want to change it or not? I don't want it to change. Okay, I will keep the second one. Do you want to change the name of the third one? Yes. To what? To A3. Yes. So in this case, we have the relation C, and the attribute is going to be the first one called A1, the second one B2, and the third one A3. So allow me to change this one. Good. If you understand this one, let's have like this complex example. So you need to wake up, by the way, if you slept somehow, sleeping somehow, please, you need to wake up here. Give you a relation instruct. Then I ask you to find the highest salary in the university. I'm going to teach you, we're going to cover something later called aggregation function. So we can use this one in order to simple way in order to answer this query. But right now, based on what we learn, we have only one option to do that, which is the following here. First, by the way, you need to understand what kind of formation you need to look for. We need to find the highest salary in the university. What's the highest salary in this university? This is Board University, by the way. The highest one is going to be 95, I guess. Yeah, it's 95. So the result is going to be here, 95,000. That's the result that you expect to get. How could you get that? We need to follow the same thing. I'm going to find the instructor salaries that are less than some other instructor salaries. So that means I need to find out a way in order to extract or derive the list of all the salary except the highest one. That's the meaning here. How can you do that? Actually, I do have example. I think prepare. Give me a second here. So you know this is step. So we're going to find the salary except the highest one. Then after that, I'm going to take the list of all the salary that we have and perform the set difference between the list of all the salary that it does include the highest one. So in this case, I end up we have the highest salary. Okay, let's just see how can you perform that. I will go over a simple example here. Here, good. So in this case, assume we have a simple relation. Okay. I'm going to have a relation I, is called I. It has the ID and the salary. And assume the ID 1, 2, 3, and the salary 1,000, 2,000, 3,000. Okay? I'm going to do what here? I'm going to create another relation. Okay? Or let's say rename. I'm going to perform this one operation. Rename. Let's say the relational structure. I'll take a copy from this relation and put this one in another relation called D. So D is going to contain what in this case, based on this command? I'm going to have the ID and the salary, the same information. The only difference is going to be the name of the relation. 1, 2, 3, okay, 1,000, 2,000, 3,000. Okay, this is the first step. Then after that, I will take D or Cartesian product with I. What does that mean? Combine, because I need to extract information based on two relations, so I need to concatenate both of them. So we have, right now, the only option to concatenate two data from two relations to use a Cartesian product. In order to perform the Cartesian product, I'm going to say this I Cartesian product with T. We're going to produce the following. Yeah, bear with me, okay? I'm going to use this one ID to say I.ID, I.salary, okay? And ID to say D.ID and D.salary, okay? With the information that we have, because you need to use the name of the relation as a prefix in order to distinguish between all the elements here. So the ID is going to be have 1,000. Let's see, you have different 1,000 here. With the value here, 1,000, 1,000. Remember, this one is going to be for with every single tuple of this relation. I try to use different colors just to show you what the difference ID is going to be. 1,000. The first one, then 1, 2, 2,000, 3, 3,000. This is the first part of the Cartesian product here. Then after that, I'm going to try to take the second column here, which is going to be for every single tuple of the relation D. So 2, 2,000, 2, 2,000. Repeat it 3 times because we have 2 tuples here each. And 3,000, 3,000, 3,000, 3,000. I want to do the Cartesian product first, okay? So this one is going to be 1, 2, 3, 1, 2, 3, and 1,000, 2,000, 3,000, and 1,000, 2,000, 3,000. Clear? This is the total when we perform the Cartesian product. Do we have a problem with the Cartesian product so far? You have to let me know whether you're okay or not. Maybe next time I'm gonna say the first one answer, I'll give him +1. Maybe. Yeah, I'm gonna do this one. Next time, the first one reply to me, I'll give him +1. So it's gonna cost me maybe 100 points. So maybe you're gonna get A after 2 or 3 class. Anyway, I do this one. Now I need to perform the second one. I need to perform the condition selection here. I do have a condition. It's called what? I need to select, as we mentioned here, we find the instructor salaries that are less than some other instructor salary. So I need just to compute it what? The first, I mean, to say, I need to find, exclude, I mean, the maximum salary. So in this case, I'm going to say the I dot, let's say, salary is going to be less than the D dot salary. If I perform this one, so we end up, and this do, I'm going to project the salary itself. I need only the I dot salary as a result. So show me whether they have I dot salary is less than the D dot salary. This one, in this case, actually this one less than this one less than this one. And this one, 2,000, is less than this one. Then after that, actually this one, yeah, 2,000. Then after that, I'm going to exclude the 3,000. So the result is going to be here either 1,000 or 2,000. All right? I said what? Project this I dot salary, where in selection, the I dot salary is less than the D dot salary. The I dot salary here is less than any, let's say, other salary. So in this case, we exclude, when we say the projection should have, we work with a set here, we don't have a duplicate of the value. So we end up, we have 1,000, 2,000, because those, in this case, the value of the I dot salary is less than any existing salary, because 1,000 less than 2, 1,000 less than 3, and this 2,000 is going to be less than 3,000. The 3,000 is not going to be part of the result because it's not less than any value. Clear? This is the part of first one here. Then after that, let's project the salary from the I. When you say project the salary from I end up, we have what? 1,000, 2,000, 3,000. I went to the original relation R, I, or D, whatever, either is fine. Project, I mean the salary here, with 1,000, 2,000, 3,000. So take this one, this relation, so we have a different color, minus this one. We end up, we have what? I'm going to remove 1,000, 2,000. The only one is going to be part of the result. It's going to be in this relation, but not in this one, is the value 3,000, which in my cases, this is the highest value or the maximum salary that we have. I know it's a lengthy process, but what we did here, just step by step, we're going to rename, create an instructor, take a copy of the instructor, rename it with the D. So we have another relation, two relation instructor and the instructor D. Before we see Cartesian product, then after that filter out the salary of the instructor that less than other salary from the relation D. Then project, I mean the instructor the salary. Then after that, project all the salary, then perform set difference with what we have before, or the result of the previous step. Okay? So I think I need to go back to the slide 52, roughly, slide 52, yeah. And that's what we did here. So if you have a time, you can follow the steps here based on this data, but it's going to take a long time because you have too many salaries when you perform the Cartesian product. It's going to be like expensive here, too much work here. So maybe you have a small number, and I exclude the name of the department because I don't need this information. I need just the ID and the salary in this case. Clear? Today, hopefully, today I'm going to go over one simple way in order to allow us in order to achieve this goal. We don't need to go over this one. We can use aggregation function and a simple function that allow me to simplify the processing. But if I don't know about them, then this is my one option in order to perform this operation. Okay? Now let's take a look to not the basic, the additional operation. By the way, those additional operations, you can perform them. You can use this using the basic operation. But maybe if you use them, it's going to simplify the process. Okay, for example, instead to say, let's say, for example, you wanted to perform Cartesian product, then after that selection, and after that you need to perform projection. So maybe in this case you can use join. This is what the join means here, natural join. And etc. So the simple way in order to produce or do the same task. If you try to use the basic operation, maybe you have a lengthy operation to perform that. Or many number of operators, you need to use them, concatenate them together in order to do that. Okay? So I'm going to take a look to the set intersection. Then after that, talk about the join. With the most important thing, we need to understand what's going on with the join. Then after that, we talk about the condition, what another type, condition join, outer join. Then after that, talk about the assignment and the division. Okay? So let's take a look one at a time. What's the intersection? The set intersection, by the way, if you try to answer this one, is like, this is the way how to write this one. Intersection with S. This actually, if you try to use this one with the basic operation that we have, can be written as follows. You take R plus S minus R union S. So you can union, then after that, produce the set difference between R plus S. I mean, this one way in order to add or perform this operation. But now, instead to do this operation, I can use R intersect with S, which is going to give me the same effect. Okay, so what does that mean, is set intersection here? Give me a second here. Yeah, I know I'm more tech file here. So this one allow me in order to what? In order to find the tuple that belongs to the relation R, and also at the same time it's going to belong to the relation S. The common tuple that appears in two relations. The same condition. The set operation must have satisfy the union compatible. They must have the same attribute degree, and also must have the attribute domain to be the same or compatible. Okay, R and S. We try to I would say, perform intersection tuple relation R, but not as relation S. The only one is going to be part of the result is alpha 2. Yeah? So it could be R. Sorry. It's going to be R, and also at the same time, it's going to be in the S, okay, because in the intersection. So the only tuple that have a common both relation alpha 2, I'm going to produce one of them, one copy of them. Okay? Because set operation here, set algebra. Let's have an example here. Find all the courses taught in both the fall 2009 and the spring 2009. So assume someone is going to say something here. Say, okay, it looks like you did a course taught in the fall and the spring. So I'm going to say here, selection. Let's say project the course ID. And you have to tell me what you think. Selection. I'm going to say, okay, this is semester equal 4. I'm just use FS to simplify it, okay? I didn't need to write everything. And let's say year equal 2009, okay? And semester equal, let's say, spring and year equal 2010, okay? From the instructor. What do you think? Let me write this one. What do you think here? So I've said, okay, the course of the semester, fall, and 2009, and at the same time, the course offered the semester, spring in the year 2010. So what am I trying to do here? So first of all, what do you think about this way? Is the right query or not? No, let me, because I said in both, must be in both. I'm trying to have in both here. So in both must be satisfy this and must satisfy this, right? If you all, this means you try to answer something different, the same thing that we use with the union. Either in this semester or this one, or in both. So course is going to be offered both. But here, when you say something like this, let me explain to you how the system is going to be execute this one. I'm going to access the relation, oh sorry, is the section here. Because information is going to be stored in the section here. So in order to access the relation, the first thing I need to perform here to what? In order to evaluate this one, I'm going to access tuple by tuple. Then I'm going to ask myself here. I'm interested, by the way, in the summer. Okay. And what else? Sorry, in the semester and the year. This tuple that I'm choosing in. So those I need to say. So that the query that you said right now, you said, I'm looking for the tuple that have the semester in this tuple, each tuple has the following value. The semester is going to be spring and the year 2009. And at the same time, the semester is going to be, the semester is going to be fall and the year 2009, and at the same time, the semester is going to be in the spring, and the year is going to be 2010. There's no way to have one tuple have satisfied the same conditions. So in this case, we cannot perform this query, because what you're doing here, it looks like you have, I want to have a student, the first name is Alice, and the last name is Bob, and at the same time, the first name is Eve, and the last name is Oscar. At the same time, no, I cannot this one, because here in the semester, when you try to evaluate this one, either I'm going to evaluate this condition or this condition. But if you said and, this means at the same time, for every single tuple, the semester must be fall and spring, and the year must be 2009 and 2010 at the same time. So this query is wrong. So the only way in order to, so hopefully you understand what's going on here. We cannot evaluate this one. So the only thing that we can do here, we're going to try to use an intersection or other set operation. So that's what we did here. All the costs that offered this year intersect with all the tuples or all the costs that can be satisfy this condition. Then after that, I have a list of costs here, and let's satisfy this condition. I need to make sure the list of costs here, they're listed here, and here I'm looking for the common cost. So here we have a cost ID that offered in this year and this semester, and offer in the spring and 2010 at the same time. Okay? Kind of. Okay. I miss online, I mean in-person class. So in parser class, I can see what are you doing right now. I know some maybe one of you said mind your business, as my kids say all the time. Yeah, they teach them the school to be independent, but this is not good for me. It's good, I mean, but not all the time. Anyway, now we take a look at the join operation. Okay, so what do you mean the join operation here? Yeah. So the join operation that we now, I don't like the way that you use the Cartesian product. Oh, sorry, the Cartesian product and cross product. Because I need to Cartesian product, then after that, I know that we have a lot of information that I don't need. So I need to make sure that perform a selection, and sometimes maybe perform what's called, projection. The join operation. This is one of the most used operator in the relational algebra and also in the database when you use the SQL later. Yeah. Okay. So this one will allow me in order to concatenate the tuple from two relations in one big relation. But now we have full control about this one. It looks like we have a Cartesian product, then after that you perform selection, and maybe you can perform projection. You see that two or more, three relations can be joined or can be combined in one operator. So that's going to be perfect. We do have two main versions in general. One is called the natural join, the other one is called theta join. Okay? Both of them, I'm going to use this symbol in order to perform, say, this is a join. Okay? So what does that mean in this case? The join in general, let me first talk about the natural join here, then one at a time. The natural join is doing what here? We have two relations, a natural join with S. Okay? So in this case, I'm going to generate a relation that contains all the tuples that are a combination of two tuples. Okay, that's what we're doing in Cartesian product, but one from ambit relation with the common values for one or more attributes. So it looks like here, in order to perform the join or the concatenate two tuples from two different relations, I need to make sure that these tuples must satisfy specific condition. Based on what? Based on the common value for one or more common attributes. So in this case, we must have somehow the same attribute in the relation R and S. And based these same attributes of the set of attributes that have the same name in R and S, we need to equate, or based on their values, I need to tell or decide whether the tuple can be part of the result or not. Let's go over this one. Assume that we have a relation R and S, and the union between of them, let's say the schema, which is, the union of both of them is going to be the schema. Of course, not the exact schema here. Let's go with this one. You have a tuple, let's say T belongs to the relation R. And we have this, let's say a small r belongs to the relation R, and tuple S belongs to the relation S. In order to perform our natural join with S, I need to have a common attributes between relation R and S. Assume that the relation R is going to contain A, B, C, and the relation S maybe has A, F, D. Okay, something like this. So we do have one common attribute with the relation attribute A here. Clear? Okay? They must have the same name. So now, in order to do the Cartesian product, we need to take every single tuple of relation R, concatenate with every single tuple of relation S, and done. Here, stop. Before you concatenate every single tuple of relation R with every single tuple of relation S, you need to check whether the value of A or R dot A, the attribute A in the relation R, or this tuple R, is equal the value of A at the tuple S. If they are equal, then in this case, yes, R concatenated with S. If not, ignore them. So in this case, I'm doing what? I'm doing Cartesian product. Then after that, I do selection based on the common attributes. Then I need to add something else. The schema actually is not going to be R and S. It's going to be what? It's going to be the attribute in the relation R and the attribute in relation S minus the common attribute. So if we have the attribute A or the common attribute in both relations, going to be appears only one time. So it looks like we add the project and we need to remove the duplicate columns out from the resulting tuples. So again, I'm going to perform natural join. That means it looks like I need to concatenate every single tuple from the relation R or the first relation with the second relation. But we cannot concatenate this one randomly. No, based on the condition. And the condition can be satisfied by what? Specified by a common attribute. The value of common attribute between both relations must be equated, must be equal. So in this case, assume that we have only one common attribute with the attribute A. That means R.A must equal S.A. In this case, yes, you can concatenate them. In order to produce the schema, we are not going to produce R.A and S.A, twice. I'm going to produce only one of them, one version. So I'm going to produce, for example, only A, which is going to be the same value. Remember, since we equate them, so there's no reason we are going to produce both of them. So the natural join will return the similar attribute only once as their value will be same in the resulting relation. Which makes sense, because since I equate them, so I know that R.A is equal S.A. So why I need to list both of them here, and both of them we have the exact value? It's going to be a waste of the time and space. So here, I'm going to only represent one of them. That's why when I say here the archer is going to be between both of them, or the degree or number two, or the schema, it's going to be the relation as R, or the archer, or the degree, how many columns, for example, 3 in this case, plus the archer of S with 3, minus M, with M, how many common attributes between R and S. If you have 1, that means the number of columns is going to be minus 1. If 2, that means we have 2 minus 2. Since we have 2 tuples, we're going to have this, or columns going to have the same value, I'm going to produce only one of them. Make sense to you guys? Don't worry, in a few minutes, then I'll give you rest. But I need to finish this one, then after that to give you rest, then I want from you to think about what's going on, what's happened, whether it makes sense or not. So this is the actual thing when I perform here. I guess we give you a relation R, example, A, B, C, D, and the relation S is going to be E, B, D. What's the common attribute here? I do have B and you have D. So when you perform R join S, this is what's going to happen here. We're going to have an A, we're going to have a B, we have a C, we have a D, we have E. Why don't list B and D here? Because we already listed them here. So that's the meaning. You're going to be only the common attribute is going to be listed only once. When you try to perform this condition here, so it looks like you're going to do what? You're going to do R Cartesian product with S. After you perform this one, you need to equate matrix, select R.P must equal S.P. For every single tuple from R must be equal, the value of P must be equal to every single tuple of P. In order to make sure that's going to be part of the result. And since we have 2 common attributes that have the same value, so I need to equate based on 2 attributes. And at the same time, R.D must equal here S.T. So for every single tuple from R, in order to concatenate with S, must satisfy this condition. Then, since we are not going to list all the attributes, I'm going to say project, okay, R.A, R.B, R.C, let's say, R.D, and S.E. And actually for the E, I didn't need to say E, because S dot, because this is the only relation, or the attribute it's clear that belongs only one relation, not 2 relations. And the same thing for C too. C here, I didn't need to say R.C, because the system knows that C belongs only one relation, does belong to other relation. So I know exactly what do you mean by the C. For A2, there is no need to say R.A, because I know exactly which A you mean. But for R.B, yes, you have to tell me R.B or S.B. Either is fine, because you know that. Yeah, since I'm equating, it's going to be in the resulting relation, going to have the same value, so either is going to be fine. Clear. And I need to add another thing here. What if the intersection between R and S equals to 5? What does that mean here? If there is no common attribute between R and S, assume that we have R is going to be A, B, C, and S is going to be D, E, F. We try to perform R natural join S, the system is going to say, okay, there is no common attributes here, right? We don't have anything. So this one, and then it's going to be degraded into the Cartesian product. So this one, you perform this operation, the system is going to end up to perform Cartesian product, going to say, this is the result that it's going to produce here. So it's not going to perform this operation, it's not going to perform this operation. Just perform Cartesian product, and good luck to you. Clear? So this is, the same thing that we talk about, different way just to talk about. This is, the thing that I mentioned If this relation doesn't have any common attribute, that means we end up we have a Cartesian product. Let me just go over examples here, then after that give you a rest, okay? So we have two relational ideas. I need to join them. I mean concatenate, by the way, perform any natural join based on this operation. So every single tuple is going to be try to concatenate with every single tuple here. But you need to make sure that with the common attribute, do you have a common attribute? Yes, we have a B and we have a D here. So in order this tuple is going to be concatenate with this tuple, the value that B and D here in R must equal the values B and D here. So B1 and DA, B1 and DA. So this is going to be part of the result with the alpha 1 alpha, okay, A, and I'm going to add only E. How about B, S dot B and S dot D? I don't need to add them because the value is going to be actually here equal. What S to B is going to be 1, and SD is going to be A with exactly the value stored here. So the natural join, well, I'm not going to produce or add them to part of the result. Continue doing this one as long as it satisfies the condition, going to be part of the result. Let's have the example using find the names of all the instructors together with the course ID of all courses they taught. We talked about this one before, okay? Last lecture actually, yeah, during the recording. In order to answer any query, you need to understand or you need to have the schema. And based on this schema, I'm going to tell, okay, it looks like in order to answer this query, I need only to ask one relation. No, I need to ask more than one relation. So in this case, you need to think about the way how can you concatenate this relation. And the best option you're going to do here using what is called the natural join or theta join, depends. Okay? So as said here, they need the name of all the instructor. So all the information so far, I can get this information from the instructor. Together with the course ID of all courses they taught. Oh, the course ID, that means I need to go in the teach, where they're going to give me all information about the course ID for every instructor they teach or taught. So in this case, I need to join both of them. So in order to join, it looks like if a join is one based on what? Natural join. And since we have a common attribute, the ID here, so this one is going to be equate every single tuple or every instructor with the list of the course they actually did teach, right? If they did Cartesian product, I don't have a problem. I need to have a selection. If they do this one, we have a problem. So when you join them here, then after you perform join, you end up, we have the ID, name, department, salary. This one is not going to be part. Course ID, section ID, semester, and year. This is the whole relation, the result relation. Then after that, what you need, I need the name of the instructor. Then I need to just project here the name. Do you need to specify or put the name of the relation as the prefix here? No. Why? Because if you take a look at the name, it looks like clear the name belongs only one relation. So I know exactly what do you mean by which name. But if you said the ID, sometimes maybe or have a relation that have maybe the name of the attributes maybe belongs more than one relation. So the system cannot tell exactly how can we get this information. So this is the natural join. The result. Then after that, after I project, the name. Yeah, they say the name and the course they teach. So I need to project the name and I need to project the course ID, which is going to be, this is kind of part of the result that you're going to have. Okay, so I will stop here. So I will back to 50. Okay, guys, welcome back. Assume that I give you this schema, which contains information about the instructor, teach, and the course. Okay. So the course contains information about the course itself. It gave me for course ID, the title, department name, and the credits associated with this course. The instructor information about the instructor, and the teacher gave me information about the course taught by every single instructor. Okay? So assume that I ask you to do the following. Find the names of all the instructors. So it looks like I can get this information only from one place for this instructor. Okay? But they said in the computer science department, yes, I can do this one. I can say select or selection, project the ID from what instructor relation and perform the selection based on what the department name is equal computer science. But they said together, I need some information with the course title. So in this case, it looks like I need to get as information for the course title. Where do I find the course title? From this relation. So I need to access relation and this relation too. Okay, of all the courses that the instructor teach. So for every single instructor, I need to find a list of the courses and I need to display the instructor the same names and also associate with the course ID. So this one is different than the previous command or query that we're looking for. Here I need just to add the title of all the course. So if we do something like this, I did instructor, natural join with teach, natural join with course. Okay, then after that, perform selection based on department equal computer science. Then after that, do the projection because I need only the name and the title. What do you think about this one? When I ask you, is this correct? 100% is not correct, but we do have an issue here. Okay, this query, the way that extracts the information like this, it works if we assume that an instructor cannot teach course outside his or her department. For example, I'm instructing the computer science department, so I'm teaching only courses that belongs to the computer science department, nothing else, so that's fine. This query is going to work fine. But if under this assumption, or assume that an instructor can teach courses outside the courses offered by his or her department, then in this case, this command is not working. And I'm trying to explain to you why in this case. So take a look first. When you say instructor with the teach, when you do the Cartesian or the natural join here with instructor with the teach, we do this one. Generally speaking, most of the operators are either going to be or the same binary relation or operations, or the operands required with the input in order to perform whatever operation you're going to perform. So you have the instructor, natural join with teach. Then after that, we're going to perform natural. The result is going to be with the course. This is one way to implement that. So when you do the instructor with the teach, I'm going to perform the natural join. The result is going to be what here? Something like this, right? ID, name, department name, salary, course ID, section ID, semester, and year. All right? When you do this one big relation, natural join with this relation, we're going to end up, we have what here? I'm going to equate the course ID with the course ID, right? And here, we do have a department name. I need to equate the department name with the department name. So, by doing so, if there's an instructor that teach course outside his or her department, this one is not going to be, this course is not going to be part of the result. I'm going to exclude this one. And the question here that I said, we need to have, let's say, all the courses, title of all the courses that the instructor teach. You understand what's happening right now, okay? So in this case, if the instructor teach course outside his or her department, this is wrong. We cannot do this one like this. Because once I equate the course ID with every single course here, and also I'm going to equate that the department name of the instructor with the course offered by this department. So here in this case, only I'm going to display the courses that offered by the same department that the instructor belongs to. So that's why I said, is this correct? So it depends on our assumptions. Whatever assumption do we have. Okay? Kind of. Good. So we talk about natural join, associative, and commutative. It's okay. Okay, we ignore the attribute orders, and also either gonna be instructor with the teach, and after that with the course, or do the teach with the course, then end up with the instructor. Because in the relational data model, we don't care about the order of the attribute of the relation, or let's say the tuples. Since you said either gonna have, for example, A, B, C, or you have a C, B, A, because we have the column name gonna be associated with every single value of every single tuple. So in this case, that's okay, regardless of the order of the columns. And also the order of the tuples, we don't care about this one. We said it's an ordered multi-set. What is the definition of the relational algebra, or the relational data model action? Now take a look to the theta join. Okay, what do you mean the theta join? That's a different way in order to perform this query. For the natural join, I'm going to match the tuples where the shared attributes are equivalent. So must we have a same or shared attributes or same attributes that appears in two relations? Then I need to equate, or the tuples will be concatenated based on the common attribute must have the same value. Here, for the theta join, you can come up with any condition as long whatever you want. So it looks like you're going to perform what in this case? Cartesian product, then after that projection. Sorry, after that selection. There's no projection in this case. Okay, so it's going to be any condition. I don't care if we have a common attribute or not. We don't care about this one. Why? Because I'm going to specify what kind of condition here in the theta. We call this one, by the way, theta join or condition join. Either is fine, okay? So in this case, we don't care. We don't, I mean, like even we have a common attribute or not, because I'm going to specify whatever kind of condition in the theta condition. So here that was some textbook, we're going to say R with S, with C, or theta is going to be the condition here with S, and here theta or C, you have to write the specific condition. And generally speaking, the predicate or the condition going to be based on what? Based on attribute in the schema R union S. So definitely going to have somehow compare some attribute from the relation R with some other attributes in the relation S. That's the meaning here. Okay? Of course, that makes sense if you try to perform condition that belongs to only one relation, so you are not going to use theta join here in this case. You have to use selection. Okay? If we have a common attribute, are we going to eliminate any of them? No. It's going to be there, exist. Even if we have a common attribute, both of them is going to be a cause. We're not going to project anything. Okay? Good. What we're going to perform here, theta join similar to what? Cartesian product, then after that selection, and whatever condition here. By the way, whatever condition you need to specify here. You can't just want basically the common attribute. Yes, fine. Similar to, yes, it's okay. But this is not equivalent to, let's say, instructor theta join or natural join with teach. That's different. It's not the same. Okay? Here is going to list the instructor ID and the teach ID in the result set. If you perform natural join, it's going to list only one of them. Okay? So this command, in order to write the equivalent command using the theta join, that's what we're going to do. Instructor, theta, whatever condition that we have, with the other relation. Okay? Let's have an example here. So again, the theta or that match, I mean, tuples using some arbitrary join predicate defined by theta here. So relational R and S here, either have a common attribute, none, they didn't care. And here, this is the condition that we have. We said R, theta join, B less than D with the relation S. So in order to concatenate every single tuple relation R S, you must have what? Must satisfy this condition. When you say B less than D, it's clear. B that belongs to relation R, and D that belongs to relation S. So where are you going to find B less than D here? B is going to true here, less than D is 3 and 6, so this can be concatenated together. And 5 is less than 6, yes. Then this one is not going to be part of the result, and this is the result you're going to have here. Okay? Clear? Okay. If the theta or the predicate is just an equality predicate, so you said something equals something else, then theta, we say condition join has a different name. We call this one Equa Join in this case. So if we have the equality, whatever theta we have, something equals something else, we call this one is like a special case of the theta join. We call this one the Equa Join. Okay, this is a different name. So here I just play around. Okay, what I did here, we have a relation R and S. I just tried to show you that. Remind you, we have a rename operator we can use in order to rename names. So I just renamed the relation S here, and I said the relation S when I say rename S. Let's say SC comma D. So what happened here with the relation S? I asked the relation S, it's going to be the same name, and the first attribute is going to be SC, and the second attribute is going to be D. This is the result of this operation. So here S is going to be equal to the following here. S, C, and D, and this is the rest of the information, the instance that we have. Clear? Then now I need to perform after that. I'm going to say R natural join C equal SC for the relation S. Now before we rename the relation S is going to contain attribute SC and D. And I say the value of C in the relation R is equal to the value of SC of the relation S. That's the condition that we're going to perform in order to have Equa Join. The only thing that we have here, this tuple is going to equal this one, because the value of C is equal to the value of SC here. Yeah, which is going to have the part of the result. There's another way to write this one without doing the renaming, because you have a common attribute. I can say R, okay, theta join, let's say R.C is equal to S to C of the relation S, which is going to produce the same result. The only difference here, we need to add another thing. We have r.c here, and here we have s.c, just in order to distinguish that we have two columns, they have the same name, but one of them belongs to relation R, the other one belongs to the relation S. Okay? I think maybe next time you're going to say, not okay. Okay. I have to say okay. Anyway, so far so good, hopefully. Do you have any question? Good. Now we're going to have something else, another join operation. So what we did right now here, in the join that we have, we just take a look to the tuples, or let's say when we perform a join in general, either it's going to be natural join or theta join, regardless of the schema, it's going to be part of the result. Each tuple in the first relation, in both the natural join or theta join, must have a corresponding match in the second relation. All right? Of course, we need to specify how can we find the corresponding match based on, let's say, the condition of a common attribute on the join or natural join, and the theta join based on the condition that we're going to specify in the theta. All right? In the outer join, in general, that's something different here. So this one, each tuple here, in the first relation, or let's say in one relation, either going to be from the left or the right side relation, does not need to have a corresponding match in the other relation. So that's confusing a little bit. So in other words here, when you perform join or outer join in general, you are going to do join, either it's going to be natural join or theta join. Then after that, you need to, depends on what kind of operation you're looking for. What is going to happen for the tuple that wasn't part of the result? Either it's going to be from the left-hand side relation or the right-hand side relation. Whether we're going to include them in the result or not. That's the meaning here. So again, so I'm going to compute the join. Then after that, you need to take a look at the tuple that wasn't part or doesn't match any tuple in the other relation. In this case, I'm not going to exclude them. I'm going to include them. It's going to be part of the result. But it depends. We have a left outer join. That means whatever I have the left-hand side, all of that tuples must be part of the result. If you have the right outer join, that means only the tuple from the right operand is going to be also going to be part of the result. Full outer join, that means in both left and right hand side, going to be part of the result. So you do join, then something extra. You need to take in account or consideration the tuple that wasn't part of the result. So in this case, I'm not going to lose information either from the left or the right hand side. When you do this operation, when you add one tuple, for example, doesn't or set of tuples that doesn't match tuple in other relations, when you add this one, so definitely you're supposed to concatenate this one with other relations. But since there is no match, you are not going to concatenate them, right? So we do have like a set of columns that belongs to the other relations that there is no expected, we don't know their values. So in this case, I'm going to padding these values with null. Okay? And we do have, when we say null, that means just tell me the values not exist or unknown or doesn't exist. We do have a left outer join, we do have a right outer join, we do have a full outer join. With example, it can be much clearer, okay? So just I want to make sure that we understand the structure here. So it looks like we perform join, then after that, the any tuple that does match, match tuple that does have any match tuple in the other relation must be part of the result, and you need to handle away the set of attributes that belongs to other relations. So you're going to be part of the result, you're going to be add this one, padded with null. Okay? We do have a three variants. We have a left outer join, we have a right outer join, and we have a full outer join. So you see, when you say this, by the way how to write this one. This is the left, this is the right outer join. That means this one full outer join. By the way, it can be natural join or it can be theta join. So you can do this something, right outer join with the theta here. Okay, and this is left with the theta join or okay. So let's take a look here. We say the left outer join, that means in this case, you are going to generate all the combination of the tuple in the relation R and S. Let's do this one. Yeah, it doesn't try to go over this one example. This is left outer join with S. So meaning that I'm generating all the combination of tuple in the relation R and S. that are equal on their shared attribute, because this is natural join. So it looks like I'm going to do equality. R natural join with S union with what? The list of the tuple plus something else. In addition of the tuple in the relation R that have no match, I mean in the tuple in the relation S, plus the tuple in R not in the result. So since you have a tuple of R, you see that if you have a tuple of R natural join S, assume that A, B, A, C, so result is going to be A, B, C, all right? So assume you have a set of tuple, both of them are the set of the R natural join S, number of tuples here. Yeah, if you're asking, I'm still not feeling well. This is the first time in my life to spend almost 1 week get sick. It's not COVID, negative. So I don't know what's going on. I'm getting older, I know. So we do R natural join with S. Now I added something else. Now, how about the tuple that in the relation R wasn't part of the result? So here I'm going to add some set of tuples here that I will explain to you in the note here. So assume that we have a set tuple that could have a value of A and B. So in the value C here, since we have a complete tuple, I'm going to fill this one with null. The positive attribute that belongs to the attribute of relation S is going to be filled with null. This is the left outer join. And the right outer join, you're going to perform the same thing. Just say right outer join with S with the same thing here. So in this case, we're going to say, for example, ABC. This is a set of attributes that are natural join with S. Then after that, you are going to include, the tuple that belongs to the relation S, not in, let's say, R natural join S. Okay, so in this case, we do have what? B and C, actually A and C here. We have A and we have C. So what about B here? The B is going to be filled with null, because this one is going to be belongs to the part of the tuple that's supposed to be concatenated with that one. Since there is no match that belongs to the relation R, which is not going to be counted here in this one. Okay, let's have an example here. So we have instructor and teach. This is a natural join. We know how to do the natural join, yeah? Based on a common attribute, ID must equal to the ID, and the teach must equal the ID in the structure. So this one, we have only this one and this one going to be matched with this. And we end up, we have two tuples. So we lost this tuple and we lost this tuple, right? It wasn't part of the result because this is a natural join. Clear? Let me do this one something. How about you set instructor theta join based on say instructor dot ID is equals teach.id. I use I and T just to simplify the process. This is instructor, this teacher. Okay? Teach. So since I'm using theta join, I'm gonna have what in this case? So result gonna be to say instructor.id name, department name. Then after that we have teach.id because this is theta join. So if I have a common attribute, I'm gonna list all of them. I'm not gonna drop any attributes. Then after that we have here the last one is the course ID. Okay, and we're gonna have two tuples here. So that's the difference between theta join and join. Let's take a look. How can you perform, let's say, left outer join? Left outer join again is going to generate all the combination of the tuple between the instructor and teach that are equal on their shared attributes. So in this case, the shared attribute on ID, which is gonna be the first two tuples. Right? I'm gonna say right. Okay. Plus, or in addition to the tuple of the relation R that have no matching tuple in the relation S. So in tuple relation R that have no matching relation S, so this tuple here can be part of the result too. Why? Because it says left outer join. So I'm not going to leave any tuple. All the tuple relation S, or the left-hand side, or the relation instructor in this case, must be part of the result. So the one that doesn't have any match is going to be included here. I include this one, the ID, the name, and the department name. Since I'm going to include both tuple, we do have a value corresponding to the course ID, but the course ID is not part of the instructor. It's going to be part of the teach. Since we don't have any match, I'm going to fill this one with null. Clear? Thank you, Yuan. Good. Now let's take a look to the right outer join. By the way, you can do this one theta join, or you can do the one with, natural join, what you're doing, and with theta join. Either is fine. Okay? It depends what you try to do here. Here, it's going to be right outer join. That means you perform the theta join, or the right outer join, going to be same as the left outer, but here the input relation will reversed. Okay? So what does that mean here? When you say which relation is going to be part of the result or not, so in this case, we have the relation structure teach, and going to perform generate all the combination of the tuple of the relation instructor teach that are equal on their shared attributes, so in this case based on ID, plus in addition to that, to the tuples in the relation teach here, that have no match in the tuples in the relation instructor. So what we have here, we missed this part, it wasn't part of the result. So this one is going to be included here. So this is a join. I use R with S simplicity. Then this one was in the instructor and teach actually here. Okay. Then after that, this is interesting here. I'm going to add this tuple that doesn't have any match in the right hand side relation. In this case, teach. I do have a course ID, and the ID and the course ID, the value. Do you have the name and department name? No, because those values belongs to the tuple that's supposed to belong to find the match in the relation instructor. Since this one right outer join. This one doesn't have any match, so I'm going to fold this one with the null value. You see that? So I'm not going to lose anything from the right-hand side relation. The full outer join is going to be union of left outer and the right outer. So you're going to be perform here instructor, natural join with teach. Then here, you're going to be say instructor and the left outer join with teach. Okay, then after that, this one is going to be instructor and instructor and the right outer join with teach. That's what it is called the for. Take everything. This one union with this with this. Okay? Good. We do have what is called the assignment operators. You are going to test and try to practice all of them during the homework, okay? Exercise. So hopefully going to help you to understand what's going on. And we are going to revisit them later when we talk about the SQL query or SQL language. We're going to go over this one again. But in that case, at that time, we're going to use like SQL command in order to access the data, etc. Okay? So we have an assignment operator. What do you mean by the assignment operator? Is that sometimes the convenience is time to write the relational algebra expression by assign box. So what does that mean here? So for example, you can divide, it looks like you have divide your write your code like sequential programs. We have step 1, do this one, step 2, this one, step 3, do this one, and every step you're gonna store the result in specific, let's say give a name to this step, or store the partial result at specific say relation. Then after that you can use them. Sometimes you can say, okay, assume that we have like this query, I'm gonna have select this salary greater than 40,000 from the instructor. I can say this one, this query 1, do select whatever from the instructor. Okay. Then after that, query 2, I'm gonna select, the salary less than 10,000 from the instructor. Then the final result query equal to what? I'm gonna say here, I will assign this one. I'm gonna query 1 union query 2. So that have a simple way or simplified version in order to write a query, especially if you have your query that contains of a lot of selection, projection, joins, etc. You can break it down in sub-queries, and then after that you can collect them. Okay. It looks like, as I mentioned, you're going to be writing sequential programming language, which you have a series or set of assignments you're going to be executing in, sequence. Then after that, you maybe have one expression that displays the final result that you're looking for. If you decide you work with this one, it's fine. It's help you in order to make sure that even if you have an issue in your command, you can't tell what's going on. We do have another way to know that. That's an example. For example, find all the structure of physics and the music department. Of course, the one that write this one, I'm gonna say what? The simple way, select the department is equal name equal physics. Actually, yeah, then after that union, that the selection, that department name, for example, equal is say music. from the instructor here. Okay? Or say this one is going to be one Q1, this is Q2, or as we did here, we have, let's say a relation name has a meaningful, it's clear to understand it's physics, it looks like instructor in the physics department, music instructor in the music department, then you union them in order to get the result that you're looking for. One interesting thing, please wake up, it's a very important division operator. So what's the division operator? So it looks like you divide something here, R divided by S. That's the meaning here. Okay? So in order to have a division operator, it can be applied if and only if you have the following condition. The attribute in S must be a subset or proper subset of attribute of the relation R. What does that mean in this case? So in this case, all the set of attributes belonging to the relation S must be exist or part of the attribute or subset of the attribute of the relation R. Give you an example. Assume R and S, these have two relations, and the relation R is going to attribute from A up to AM, then B1 up to Bn. So we have many attributes. Relation S is going to be B1 up to Bn. You see that all the attributes of relation S is a proper subset of the relation R. So in this case, when you divide R divided by S, so it looks like you take the relation R and divide by the relation S. So in this case, it looks like you remove all the attributes from the relation S, from the relation R. And you end up, we have the part only from the relation R, the set of attributes of the relation R, but not in the relation S. That's the meaning of division. Okay? So end up, we have this schema R minus S, which is going to be a part of the attribute only belongs to the relation R, not in S. So why we need this command? Okay? This command is going to return as what? So it's going to, this relation, when we perform R division by S, or divide by S, or divide by S, it's going to be returned to say a relation that will have only the attributes that in the relation R minus all the attributes in the relation S. So that's what we did here. And the relation is going to return by this operator, it's going to will return only the tuples from the relation, let's say in this case, R, okay, which are associated with every S tuple. In other words, when you say the question or command asks you, for example, looking for all, looking for every, all, courses, something like this, so in this case, you can think the best option for you in order to perform this operation using the division. Let's have an example first. So in this case, assume that we have like, I'm looking for the list of all the students who have taken all the courses in the biology department. That's what I want to do. List all the students who have taken all the courses in the biology department. So I'm going to do those the following. First, I need to project the list of all the courses taken by every single student. So I will tell you the text which contains all the information about the course taken by every single student. Then after that, I just project the ID and the course ID. So here it's going to say, give me the ID and the course ID. For example, student 1, CS425, student 2, CS552, 3 or 1, CS110, whatever. Give me a list of courses for every single student. Clear? Then I'm going to go to the course, okay? And from the course, there contains information about the courses offered by every single department. Right? Then I'm gonna select all these courses, the tuple that satisfy the condition biology. So I list all the courses offered by the biology department. I need only the course ID. So here we do have two relations. One contains all the courses taken by the student. The second contains all the courses offered by the biology department. So in this case, in order to answer my query, list all the students who have taken all the courses in the biology department. I can perform this one using division. Take all the courses that, for example, are divided by S. I can't do this one. Why? Because the attribute relation S is subset or proper subset of relation R. So this case is going to produce, when we perform this operation, going to produce the tuple, and the, let's say, tuple T, okay, where the tuple T belongs to what? The project R minus S from the relation R. So in this case, you see that I'm not going to tuple, it's going to contain all the information that contains the relation R. Only the set of attributes that belongs in the relation R, but not belongs in the relation S, because when we perform the division, it looks like we eliminate them. You see that? For example, A1 up to A. Okay? So it's going to be part of the tuple. For example, it's going to be the student ID. Okay? Who has satisfied this following condition, and that's what we did here. For every single tuple belongs to the relation S. We use this one U. In this relation, for list of the course offered by the biology department. In the way that must exist the following. I'm gonna add T, which contains only the list of tuples that belongs to attributes that belongs that have, the set of attributes belongs to the relation R, but not belongs to the relation S. With the U, which the set of attributes belongs to the relation S. If I concatenate both of them, it looks like I can generate the tuple that belongs to the relation R, a full tuple. Okay, so that means here, for this case, that means in order this student can be part of the result, this student must satisfy the following condition. Student ID take a course, and the list of the courses taken by the student must be listed here in the whole relation S. It's confusing a little bit. Let's have another example, then get back to this one. Let me do this one first. I give you the relational reads and newspaper. This is the relational reads, that's name and newspaper, and this is newspaper. Okay, another relation. Then I ask you to find the name of all the person that read all the newspaper. All the newspaper. So what are you planning to do here? What's the old newspaper? The newspaper that we know we have Times and Wall Street. Okay? So in order to find the person that satisfies the condition, that means in this case, I'm looking for someone here in the reads relation that has a name, for example, any name, and this guy read every single newspaper, Times and Wall Street. So that means in order to have this one, gonna be part of the result, gonna be whatever the name here, let's say X, and this name gonna be has a tuple, has a Times, and this X is gonna have another tuple, and the newspaper value is gonna be Wall Street. If I found this X, any one name satisfy this condition, this is gonna be the result that I'm looking for, part of the result. So you take a look at beta times. You check this one. When you divide this one, it's going to be T. T in our case is going to be beta. Okay? U is going to be Times or Wall Street. T and U, that means we must exist here for every single value of the U here. We must have a tuple. So we're going to have a beta and Times. And we must have a beta and Wall Street. Do you have beta and Times? Yes. Do you have a beta Wall Street? No. So beta is not going to be part of the result. How about Bob? Do you have a Bob Times and Bob Wall Street here? No. How about Alice? Do you have Alice Times and Alice Wall Street? Yes, yes. So Alice is going to be part of the result. That's the meaning here of the division here. So again, the definition here, in order to divide the operator between R and S, two relations, can be applied if and only if the attribute of the relation S is a proper subset of attribute to relation R. The relation returned by the division operator will have attributes that all the attributes in the relation R minus all the attributes in the relation S. So in this case, it's going to be all the relation R, but not in S. So in this case, only the names, yeah, because the newspapers belong to the other relation, right? And also, the relation returned by the division operator will return those tuples from the relation here, reads or R, which are associated to every single tuple of the relation S. So in this case, if I have associated with every single relation S, so this one can be part of the result. Because all. Clear? Please, that's clear. Okay. How about the rest? The class. Let's do this one again. Assume that we have to try to find this one. As we said, R division S. Divide by S. Or you need to divide the division. So in this case, you're going to perform this way. First, check the condition. Whether R the set of S is a proper subset of R or not. DE, DE. Good, perfect. So the result when you perform this one is going to be only the tuple that attribute belongs to relation R, but not in S. So A, B, C. Good. For every single tuple of relation S is going to be part of the result. That means the set of attributes of the relation R, okay, which are associated with every single tuple in the relation S. So here, in order this one is going to be part of the result, that means we must have in this relation what? A tuple that have alpha A alpha and the value of D and D A1. And also, we have another integer alpha A alpha and the tuple or the other value for the D is going to be B1. If you have two tuples, then in this case, yes. So check alpha A1, alpha 1, yes. Did you check this one? Do you have alpha A, alpha B1? No. So this one is not going to be part of the result. Take a look at the next one. And all this one is going to be all the value here, satisfy all the values here regarding whatever course offered by the biology department, whatever it might be regarding the value is going to be the list of all the magazines. So we need to find everyone who wrote read every single magazine. Yeah. So alpha A gamma. Alpha A gamma. Do you have alpha A gamma A1? Yes. Do you have alpha A gamma B1? Yes, because here. Then done. If you have another value, I didn't care. The most important thing must have this satisfy this condition. So alpha A gamma is going to be part of the result. I will do this one, then I will stop. Beta A gamma. In order to be part of the result, must have A1 because the value here for the DE. Then we must have beta A gamma with the value A, B, C equal this value, and the DA must be B1. So alpha beta A gamma A1, then beta A gamma B3. So no, then this one is not part of the result, and etc. That's the meaning of that. Help us a lot to hopefully understand what's going on here. Okay. Now we're going to talk about something different. We're going to talk about what is called the extended relational algebra operation. So what does that mean in this case? And this is, I'm going to show you a different relational algebra, okay, that provide the ability to write a query which we cannot express using the basic relational algebra. So I'm going to talk about the generalized projection, then aggregate function. Remember, we talk about the minimum, maximum value, etc., which is here part of the aggregate function. So let's take a look first. What is generalized projection? So we do have a projection, we said so far, projection A, B from the relation R, set of attributes. That's the basic normal way in order to use, or the simple way to use a projection, right? Now we're going to talk about something different here. I'm going to see, maybe you can still do some arithmetic function. For example, you can say project, that's the meaning of generalized projection. You can say A multiplied by 2, divided by 2, or 20, whatever, divided by 10, something like this. Then after that, you can assign this one, say this result is going to be X for the relation R. So you can perform some arithmetic operation here, or expression function over the attribute itself. You can say, for example, project A plus B, and of the relation R, and you can rename this one, assign another name. Maybe result is going to be R, or result. Okay? Or you can, in order to rename this one, either you're going to use an arrow or use the S here. So that means whatever you have an expression here, you can be renaming as another name. What does that mean, renaming? That means when you display this one as a result, you see this, the name of the column is going to be equal to this name that you specify. Clear? Let's have an example. Assume give you the relational, say, credit account, which contains information about your credit card information. Of course, you have credit card information not symbolized this. So we have a credit ID, we have a limit, and we have a balance. We have three attributes here. And I ask you a question, compute the available credit for every credit account. Okay, what is available credit? Available credit computed as follows. Take the limit minus the balance, then there's going to be available credit. So in order to perform this one, you see what you're going to do here. Of course, it makes sense to show me the credit ID, then let's say the available credit for this credit ID. So you perform projection, credit, or let's say this one, credit ID. Then here I'm going to take the limit minus the balance. And if I didn't rename this one, so I'm not sure what the name is going to be here. So that's why it's better when you perform any mathematical expression over any attributes, it's better to rename this one, give it a name. Because it's unpredictable. I don't know exactly what's going to be the final result, what's going to be the name of the relation. If you didn't do this one, I'm not sure what's going to happen here. What's the name here? Might be going to be mostly the case limit minus balance. Something like this. So it's better to rename this one. So whatever, compute the limit balance for every single tuple that we have, get an input, compute the value, and answer or put this one under this attribute. So result for every single credit ID, this is going to be the available credit based on the value that we have in the limit and the balance. So that's great. We can control the outcome of the result that we have. We can perform some arithmetic function or relational operation. You can multiply by the constant, divide by whatever you want, whatever kind of operation you can perform here. Let me give you another example here. Let's talk about you do have the instructor ID, name, department, salary, and assume the salary as you're given in this relation or this table is the annual salary, and I want to compute this the monthly salary. In order to compute the monthly salary, so it looks like for every single instructor, you need to display the ID, comma, you take the salary attribute here and divide it by 12. Assume that the monthly salary in the 12 months X. Okay? So in this case, you have project ID. For example, if you want this rest information, depends on you. So I'm just care about the ID and then take the salary divide by 2. And I prefer to rename this one. Remember, either going to use as, new relation, or you can use the right arrow. Okay, in order to specify what's the name of this attribute. So this one is going to be the bottom of the result. Is going to be have the ID, name with the outcome, and we have a department name. Then we're going to have here the monthly salary. So we have these columns, and this is the result going to be whatever the value going to be. So there. Okay. Let's say monthly. Clear? Kind of. Aggregate function was very important here. So again, I ask you to wake up 3 times. This is the first time, the last time that I want from you to wake up. So what do you mean the aggregate function? Remember, I will ask you to try to compute, say, the highest salary or the maximum salary. You did a lot of operation in order to get the maximum salary. We do have an easy way in order to perform that. So aggregate function was and very useful, allow us in order to compute, to apply a function to a collection of values, to a collection of attributes. You specify to the column, you can specify to which, you can divide your data into groups, then you can specify or come up with the whatever aggregate function you're going to compute. When you say aggregate function, allow you to take the set of values, okay, and returns a single value as a result. So you can compute the minimum. We do have either the sum to values, you can compute the minimum value, the maximum value, based whatever attribute, you can count the number of values, you can compute the average and the sum, which is interesting. You're not going to, you just use this function and the system automatically do that. So the way that organizes one, this is the way how can we write the aggregate function. So you have whatever expression, relation, perform query, whatever. Then you can use calligraphic, G, just to specify this is aggregate function. Some text box are going to use gamma. Either is fine, whatever you want to use. Okay. So in this case, we do have like you can specify group your data based on sub attributes. Then after you divide them, so it looks like in Excel. You can say, for example, I want to count the student. I mean, for example, let's see, do this one. I need to count the students each about that enrolled in this class. So for example, you can say the department, name, and the second column give me the number of students, enrolled or number, right? Department 5, 6, computer science 1, math 2, and etc. Something like this. How can you build this one? So I'm going to say, okay, I'm going to organize my data group, my data based on the department. So in this case, I'm going to say based on department name. You take my data, for example, the student enrolled in this class, assume it's going to be in the relation R. You take the relation R, divide it based on the department. Take each student that belongs to the same department and get be grouped together. So they have groups computer science, we have a math, for example, and etc. Okay, that's what I did when I say department name. Calligraphic, G, and here what function I need to compute? I need to compute the count because I need to count how many students. So you can use a count here. Over what? You can count based on the student ID, for example. Whatever attribute, or you can count star. How many tuples exist in this each subgroup? That's the meaning here. Either is fine in this case. Over the relation R. Okay, and this is my command. This is going to compute the count, the ID, so it's going to display the result for divide the data based on the department. Each one is going to be count or perform whatever operation here you're going to perform. Clear? This is one simple example here. So let's take a look here. Give you this relation, and assume that I need from you to compute the sum of C, okay, over the relation R. So in order to compute the result, did I ask you to group them based on any attribute? No. That means you're going to perform the whole operation or this aggregate function based on the entire data. So assume all the data is going to be one big group, okay, or giant group. So in order to compute the sum here of what? The whole relation, and I said sum of C. So in this case, the result is going to be only one tuple, one column, one value, okay, because you have only the sum, there is no group, and also you're going to say based on sum of C, so add up the number of C's. Let's play around. How about if say, okay, how about if say A, calligraphic, you say sum of C of the relation R. What the result is going to be here? So in this case, it looks like in the system, going to say, okay, I'm going to classify this one based on the attribute A. So here, one group and this one group. For each group, you're going to apply whatever the function that we have. So for each one, going to be here, the result is going to be A, okay, and it's going to be the sum, C. This is the result. We have two tuples. The first one is going to be the value of A is A, alpha, and the second one is going to be this value of A is beta. And the sum of C here for A is going to be 14, and the sum of C, let's say, based on the second group, is going to be 13. So you classify your data. Let's add something else. How about the same max of C? You can do this one. That means we have another column here. It's called max C, and the result, what's the maximum of C is 7, and what's the maximum C of the second group is going to be 3rd. And you can comma, you can add the minimum, you can do whatever you want. We prefer when you use aggregate function, etc. It's better to rename them, because right now maybe the name is gonna be the name of whatever function or aggregate function you're gonna use. But it's good practice when you say, for example, calligraphic, you say sum of C. I can rename this one as a summation, or let's say the total, for example. Yeah, let's say total. Okay, over the relation R. So that's good practice, or use as. Okay. Give you the relational structure here and ask you, please find the average salary in each department. So it looks like we say in each department, you wanted to divide your data based on the department. And for every single department, you need to compute the average. How can I divide my data based on the department? So in this case, all the information from the relational structure, I need to aggregate perform a group by the department name, perform the calligraphic, and here in this case, symbol for the G. And then here I need to compute the average salary. And actually here, the average salary, I need to rename this one as a salary. Or as here as a result, you have to say this is the average salary. Okay? So you divide your data, your department. So that's what we did here. This is biology, this is computer science, this is electrical engineering, history, finance, and physics, and music, and etc. Okay? Now for each of them is going to be compute the average. Average what? Of the salary. So you have to specify what average, which attribute you need to perform, apply this operation based on. Okay? So for each department, I'm going to produce this one. So the department name, compute the average salary, computer science, and compute the average salary for these three attributes and so on, or three values. It's not hard to use them. It's easy. But you need to understand what kind of operation, what kind of aggregate function you're going to perform, whether you need to classify data based on what attributes. Okay, and again, you can use all of them. You can compute the average salary, you can compute the minimum, comma, the maximum, comma, whatever. Okay? So this is just as I said, I need to include the name of attributes after I perform the aggregate function. It's better renaming this one. Either you will add or maybe use the right arrow in order to rename it to the different thing. Good. That's all about this data. I mean, performing, let's say, select or perform a query. Now let's take a look at the way how can you modify the data? What if I wanted to change something with the data that we have? When we talk about the data, I'm talking about the relation itself, about the instance, okay? I'm not talking about you're going to change the schema structure, etc. No, only the instance. For example, in order to perform insert, delete, and update. So the first one, generally speaking, all of them, insert, delete, update, somehow can be expressed as following. You can use assignment operator as following. You're going to perform operation in the old relation, and you're gonna instance and store the result or modification to the new one. So the right hand side, you do minor modification, whatever the data, all the relation, and the result can be stored in the left hand side. Okay, let me give you a simple example. For example, when you try to write a query or search a query, result in the set of tuple to be inserted. For example, you want to insert something in the relation R. So you take the R, this is the old new value, take the old value, union whatever expression that we have, whatever query that you're gonna produce. For example, I wanted to insert a new, let's say, instructor or new student. What kind of new student? So I have to specify, give me what the value that you want to insert here. We have one notation you need to follow here. Let's say if you have a string, varchar, etc., you put this one between single quote, the value. That's what we did with the clock. So you know the student contains the student ID, name, department, and the number of credits, I guess. Yeah, the total credits the student has passed so far. Okay, so in this case, I add to create this one, or maybe it can be like result select whatever from the relation R, whatever you get this one, it's gonna be union with the student. So whatever the old value, I'm going to add a new tuple that contains all the attributes, and we put this one in the student relation. This is how can you insert. Sometimes maybe insert requires you to perform multiple operations, but in this case, a simple case, you just add a new tuple to the student relation. How can I perform delete? Oh, delete, assume that the university decide to delete instructors with the salary over $1 million. I don't know how this instructor, but let's say something like this. So if you are trying to perform this operation, in this case, I'm going to use here the set difference, not union. Union, that means you get combine, yeah, or add. Set difference, that means you're gonna eliminate whatever you have here. You have to remove from the left-hand side relation whatever you have in the right-hand side relation. So in this case, I'm gonna select get all the information about the instructor that satisfy the condition that's greater than 1 million. This is gonna be a list of them. So small relation, have the same structure, add the structure relation, then take whatever you have in the structure and you remove these guys from. That's what we did here, minus. And store the result, the total result will be stored in the relation instructor, the same relation. Remember, whatever can be old relation will be stored in the new one. Okay? Update. If you try to perform update of the relation, so in order to do update, generally speaking, if you try to update an attribute, we cannot do that. ID, I'm talking about here for the relational algebra. For example, ID name and the department name, for example. You want to change the name for a specific instructor or specific student. I cannot just modify one tuple, or let's say one column or one attribute. So in order to do this one, for example, student 1, Alice, computer science, we need to modify the name is not Alice, it's Bob, for example, or whatever. Just modify the data, update data, or columns, okay, or set of columns. So in this case, the only option left to me, I'm going to delete this guy from the relation. Then after that, I'm going to insert a new tuple that contains information that's going to be the same information, except you need to update whatever value you wanted to update. For example, it's going to be Bob here, and the computer science. Then I'm going to delete this one. Then after that, you're going to perform insert. It might be in this case when you delete something, when you talk about the deletion here, maybe require from you to delete data from multiple tuples. Multiple relation, not one relation. Two more things. Actually, we're almost done, but for this part today. So we're going to talk about the equivalent queries. What does that mean, equivalent queries? So there is sometimes you're going to have different way in order to write your query. Okay? So assume that I ask you to find the instructor in the physics department with a salary greater than $90,000. So we have one way to do that. For example, you can say select the department name for physics and the salary greater than 90 from the instructor relation. This is one way, or this square one. The other query, you can wait to perform do the selection first over the instructor that's greater than 90,000. Then after that, I'm going to perform selection over the filter out the department physics. In other words, you take a look at both of them, they are, let's say, equivalent, but they are not identical. Identical, that means you are not going to perform the exact step in order to perform the result. Equivalent, that means regardless do Q1 and Q2, I'm gonna get the same exact result. That's the meaning here. So there's an equivalent. Okay. So if you take a look at more details here, how it's gonna be from this one instructor, and here you're gonna be from the department name, whatever, and the salary is greater than 90,000. Get the result. Or you're gonna ask the instructor. You perform selection department first. Then after that, you perform the selection with the salary greater than 90,000. Then here at the top, it's gonna have the same result exactly at the top. So that's why we say this equivalent, but they are not identical. The same thing here. This maybe is gonna be interesting to take a look here. So the first one here to take a look is to select the department. Ask you, for example, find the information about the course taught by instructors in the physics department. So in this case, you have course taught by instructor. That means you need to access the data that belongs to relations, which is in this case instructor and the teacher. Right? Perform natural join or theta join. It depends what you're planning to do here. Assume that we're going to use a theta join. I need to equate based on the instructor.id equal teacher ID. Then after that, I'm going to make sure the selection of the department will be physics. This one way. Another way to do that, first, I need to find out the list of select all the department name equal physics from the instructor. Then after that, I'm going to perform this one, perform the natural join. So you take a look at the second one. Only to show you the first one. Instructor teach, theta join, based on the condition. Then after that, selection department equals something. This is query 1. Query 2 here, can do the difference here. We have first taken instructor. Then after that, you have performed the department selection, filter out the totals based on the physics. Okay. Then after that, you're going to perform theta join with the relation T. Both of them are equivalent, they produce the same result, but they are not identical. That means the cost of order to perform both of them are not the same. Actually, we prefer use this one. Later we talk about the query optimizations. Actually, we cover this one in CS4 5 to 5 more details. We take a look here the way that when you try to execute your query, so step by step. So this one is going to be ask first the relation I, try to reduce or filter out the N1 to tuple. So when you perform selection, in most cases scenario, you're going to reduce the number of tuples. Assume that we have 1000 tuple relation I and 1000 tuple relation S. If we perform Cartesian product here, we have 1000 multiplied 1000. So here we get a 1000 natural, or we say theta join with 1000 tuples. Then after that, perform projection, selection, then produce the final result. Assume the final result will be have only 100 tuple. Assume that in this case, when you perform 1000 tuple, access the selection department name is equal physics. You filter this one of selection over the relation I. Instead, you have 1000, you end up maybe have 500. Maybe it's going to be reduced, or maybe 50, something like this, whatever we have, okay? Maybe 50. Then after that, we have 50 natural join or theta join with 1000 is much faster than if we try to join 1000 with 1000. You see that that's the way that when you talk about the equivalent, because in the query database management system, you're going to do what is called the query optimization, come up with the query that we have, try to figure out the best way in order to execute the query. What's the cheapest way, what's the fast way to do that? Okay. So that's what I've said here. The database for the part of I'm not going to say the part of relational algebra. What the relational algebra notation, I'm going to tell exactly what I need and how can we perform this one. How can we access this one? So both of them here, they are equivalent, right? They're going to compute the query here. So they're going to show you the high steps. Which one is going to be faster? It depends on the data that we have here. Okay. For example, if we have an index based on the attribute ID, so I can use this index. So far, we didn't talk about the index, but index like a special data structure we can use in order to expedite the access to the data. Speed up, find where my data that I'm looking for. Instead, we access on trial relations. So this one's going to say, oh, you want the data, your data is going to be found in the data block. Fetch that one. There's no need to waste your time. Okay? So anyway, for the relational algebra, I'm going to give the actual step, what I need the result, and the actual step. So it's not like kind of abstraction. It looks like some structure we try to use if you apply your relational algebra and use it the way that in order to communicate with the database. We are going to use some abstract. It's going to be de facto the standard, or some standards called the SQL or SQL. SQL query language, which allow me in order to what? And just to tell the database that's what I want. Then after that, feel free to figure out the best way in order to execute this one. So that's perfect. That's going to be big plus in this case. Okay, so this is the end of the chapter 2. So that's what we cover. I mean, we cover the introduction, we take a look at the relational data model in general, we talk about the formal, let's say, relational language. Now we're going to take a look now, the good thing, which we're going to use in phase 1 and phase 2. How can you design my database? Right now we talk about the database. We said university database that contains a student, instructor, that contains, let's say, teach, takes, etc. And each relation is going to have specific attributes. The question here, from where these attributes came from. How can you design my data? If we give you like a description. If someone hire you and said, I want from you to build like a database system. So the first thing you need to do here, there's many steps we're going to cover in the database design. The simple one, you need to gather information to get whatever these guys wanted to do. Then after that, try to figure out the way how to represent them in a high level format. Then after that, you're starting doing some implementation. Yeah, how to convert this one. This step is going to be covered in the database design. Then hopefully next week, I think I'm going to spend the next lecture to cover database design, because here we do have 2 parts. The first one, I'm going to talk about the ER model with the way how to design the data abstract form way. Then after that, the second one, which is going to be phase 1 with the class project, and the second one is going to be how can you convert the ER model or diagram into the, say, relational data or into the relational database. The same one that we use, you're going to see that you're going to have tables, set of tables, each table will have a set of attributes, which is going to be the phase 2. Hopefully it's going to be finish this one in this week. I think I do have maybe a few minutes. I think I'm going to stop here right now. Okay, so see you in Thursday.